Okay, so what we will do is we will use the day 2 part of the Discord unless you you know aren't able to get on there, in which case you'll just do it on Zoom. I'm kind of like collecting everything and like dumping it on I'm collecting the Discord the Zoom chat. Zoom produces it. And so I'm putting it on Discord, but I'll also share it uh, with you by email somehow. I got to figure out how to get it to you. I guess I could just like, otherwise it'd be like a massive thing. So something you might want to look at is we have this AI companion and at the bottom, and you should be able to ask questions to the AI companion as it goes. The AI companion, as I understand it, is transcribing using a transcription service. It's transcribing everything I'm saying. And then it's got a large language model. I don't know which one, but it's got some sort of large language model that then searches over what's said. So you should be able to do something. I don't know how good it is, but even these even things like GPT-3 or those equivalent are still pretty good. And we're going to do that. So what we're going to do is two things. We're going to spend the 45 minutes doing the homework assignment together. All right. And I'm going to first do the Excel spreadsheet because I think actually probably the Excel spreadsheet might be the easiest thing to kind of do together. And what I've done is I have uploaded the solution key. So if you go to Causal Inference 1 lab, here is potential outcomes. I got the solution key and I got the raw one. Okay. So I'm going to not do the solution key, but you've got it. Okay. All right. So we're just going to fill this out. All right. We're going to fill this out and just make sure that we understand one more time the decomposition. All right. Fill out your treatment effects. We've got perfect doctor assignment. Okay. Got perfect doctor assignment, which is going to be if perfect doctor, as we've described it, perfect doctor treated if and only if treatment effect is 0 or positive. Okay. So that's negative, negative, positive, 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 negative, 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 positive. So look, because the treatment, now I've got exercise and mindfulness. So because the treatment effect is calculated as the difference between Y1, Y0, okay? And for those that weren't here yesterday, Y1 is your health outcome for this person had this person receive that treatment versus health outcome had this person received the control. Just call it the control, right? But we're going to have it be like they were all coming in doing mindfulness, but maybe this person gives them exercise instead, Okay. So the perfect doctor knows the treatment effects. Nobody in the real world knows the treatment effects. Okay. So people always ask me, how do you know this? And the answer is this is make believe. This is a spreadsheet meant to simulate treatment effects so that you can do the decomposition. Okay. So here we have perfect doctor treatment assignment. So let's fill out, before we do this, let's go ahead and fill out our aggregate parameters. All right. So average treatment effect, the average for all people. Okay, so ATE, average treatment effect for the entire population. ATT, average treatment effect for only the people who got exercise. And the ATU, average treatment effect for only the people who got mindfulness. All right. So it's these two right here will depend on the treatment assignment. That one never does. The average treatment effect is independent of the treatment assignment. So now we're going to go equal average here. All right. And you can see under this kind of perfect doctor situation, the average treatment effect, the average treated on the treated is always going to be positive, and the average treated on the untreated is always going to be negative. But that's the only reason it's like that is two things, because there are negative treatment effects, and because there is negative and positive, and treatment assignment is based on the treatment effects as opposed to just one of these. See, so you can have selection on that. You could have selection just on that. You could have selection on that. They're going to all be a little different. Okay. So now we're going to calculate our expectation Y0 for the treatment group. And when we do that, this is how we're getting our selection bias term. We go here, 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 here. Then we go for the control group. Here, 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 here. I actually think I did it wrong. Yeah. For the treatment group, we go here, 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 there. All right. So this is the average health outcome if you were on mindfulness. Okay. Average health outcome if you're on mindfulness. X, Y0, D equal 1. This is the average health outcome on mindfulness for those on exercise. Counterfactual, but real, but fixed and quote real. It depends on what you mean by real. Then we have expectation Y0, D equals 0. This is the average health outcome on mindfulness, which is the state of the world. For those on mindfulness, which is, a particular subpopulation. Okay. This is observed because Y equals Y0 if D equals 0, but Y equals Y1 if D equal 1. So that's why we do not see Y0 for D equal 1, which is that, B16 cell is technically missing, but not B17 cell. All right. Okay. So we do that. And then we take selection bias, and then selection bias is expectation Y0 D equal 1 minus expectation Y0 D equals 0. And it just measures the differences in the two groups, average Y0. That's all it is. It's just a difference in the two groups had both of them been on mindfulness. Equal. So if the treatment group had been on mindfulness, they would be particularly less happy. This is a group that is very unhappy on mindfulness compared to the mindfulness group. Okay. Then we do equal average. We calculate the percent of the population in the treatment group. This is the percent of the population. Pi is percent of the population in the treatment. That's weird. Why is that happening? Okay. All right. And then the STO. We're going to do the STO two ways. Okay. STO direct, average Y for D equal 1 minus average Y for D equal 0. It is simply describing how the two groups differ on happiness. That's all it is. equal average. Oh, we never did this. So we got to do this. First, we got to go switching equation. We have to assign potential outcomes to realized outcomes using treatment assignment. Okay. And that's going to be y equals dy1 plus 1 minus dy0. You know, put the equation in. Equal d times y1 plus 1 minus d times y0. Okay. So all that it's doing, all that it is doing is it is assigning to reality one of these. So if he's on the control group, his realized outcome is y0. But if he's on the treatment group, his realized outcome is y1. It's all that it is. Okay. All right. So then we go down here. Now we calculate the STO, and it's only going to be right here. Equal average. This minus average. This, that. Okay. Negative 0.29. Exercise group has exercise group's realized happiness is 2.97 points lower than mindfulness group, even though the ATT and for that group is 4.4. But the ATE is negative 1.54. So it's a biased estimate of the ATE. All right, because it's biased because it came out to be negative 2.97, but the average treatment effect is negative 1.54, and the ATT is 4.4. So it's a bit misleading. It's not terrible. It's getting the sign right, but it is a little bit misleading. All right, so we're going to do now STO decomposition, which is AT. So it's STO equals AT plus selection bias plus 1 minus pi ATT minus ATU. It will give us the exact same number as STO direct, i.e. negative 2.967. Okay, so let's do it. Equal average treatment effect, selection bias, 1 minus 4.54 times ATT minus ATU. And if this is not identical, you made a mistake. There it is. Ah, thank you. Thank you so much. Okay. So you can see here all that this is doing. The only purpose of this exercise, well, is the two purposes of the exercise is one, to decompose all simple comparisons into treatment effects and bias terms. That's one. And the second thing is it helps us understand why randomization will be so important. Randomization will delete the selection bias terms and the heterogeneous treatment effect bias term. Okay, that's what it does. But without randomization, you will always have, without randomization, you will always have STO equal the thing you're trying to get plus bias. There's our bias right there. So our goal, as much as we can, this is what my colleague Mark is always saying. He's always saying, try to find the coin flips in your data. That's what he's always saying. Try to find the coin flips in your data. Why? Why do you want to try to find the coin flips in your data? Because coin flips, as we're going to see, delete selection bias and delete heterogeneous treatment effect bias such that even simple methods will recover causal effects. All right. Okay. So let's stop there. We can do this one, but you've got the solution key. Does anybody have any questions about this? I'm going to upload this so that you can have what I just wrote. But while I'm doing it, does anybody have any questions? Yeah, I can totally do that. Heterogeneous treatment effects. Heterogeneous treatment effects. First, let's write down what it is. Okay. SDO equals AT plus selection bias plus 1 minus pi ATT minus ATU. All right. So ATT. Assume that people who go to college see a 10% increase in wages, causal effects. Okay. ATU. Assume that people who did not go to college would have gotten a 2% increase in wages, causal effect. Okay. ATT minus ATU would equal 10% minus 2%, 8%. Okay. There is different returns to the treatment for the treatment group than there is the control group. It recognizes heterogeneity in the treatment effects. Now, it could be ATT equals ATU always, because maybe there is no heterogeneous treatment effects. Maybe everybody has a causal effect of 10%, in which case ATT minus ATU equals 10% minus 10% equals 0%. So it's not guaranteed to be there. Where does heterogeneous treatment effects come from? It came from this. Came from what we did yesterday. All right, there it was. Here. Remember when we did this? All this stuff? Remember this? So we wrote down the definition of the average treatment effect. We broke the average treatment effect into weighted averages, and then we wrote down the weighted averages using the definitions, changed out the letters, rewrote it again, added in some zeros, moved it around. SDO equals C minus D plus all of that. We summarized it by pulling out the 1 minus pi. We left with this. Rewrote it. SDO, average treatment effect. There's selection bias. There's the ATT times the share of the units in the control minus there's the ATU times share of units in the control. Rewrote that. There it is. It literally comes out of the definition of the average treatment effect. It's where it all comes from. It literally, we took the definition of the average treatment effect, rewrote it as a weighted average of the two causal parameters, and then wrote down the definitions of both of them. And it just was, that's the definition of the average treatment effect. It's the sum of all those. And then it was just all it was a matter of just plugging in some zeros, rearranging it. It's all that it ever was. And at that point, we can now peer inside the SDO for the first time. And when we peer inside the SDO, we see that the SDO does equal the average treatment effect, but it's also biased. So you see, Julietta, what you've got to do in order to really understand it, what you've got to do is you've got it. There is nothing more important than going through these 4 slides with a pen and paper and going through each equation and not going to the next one until you understand that line. You got to go through it. You got to go through it. And I had to do that too. And that's why in the book, I gave all the steps because I knew that people needed to see all the steps, but you've got to go through it. It comes right. That's the thing. It comes out of the identity. It comes out of the identity. It's just flowing out. Oh, you're saying how does different units react to the treatment? I don't know. This is the point, Julietta. The point here is that potential outcomes framework does not make prior statements about what treatment effects can be. It basically is theoretically agnostic. It's theoretically agnostic. It just says, maybe it could be. Maybe it's the same. Maybe it's not the same. Who knows? There could be a person that's just, Mark Zuckerberg. What would have been the effect of Mark Zuckerberg to finish his Harvard degree? It'd probably cost him about $100 billion. Because if he had delayed at all the creation of Facebook, given that he was in a race with someone, it very well could have hurt his wages. Whereas most people, it helps. There's all kinds of stories like that you could tell where there's differential responses to the treatment. They can have social scientific explanations. They can have more rooted explanations. Okay? So we just allow for the possibility when we wrote it down like this, we are basically upfront saying anything. This can be anything. Okay? Does that make sense? Okay. That's really kind of an important point because this is a criticism of the potential outcomes. A criticism of the potential outcomes is that it is so agnostic about the theory. Well, we're not covering marginal treatment effects, Eduardo. It's a part of the instrumental variables literature. And so it's just kind of too advanced to cover. You can get it. You have to estimate a propensity score. You have to have a continuous instrument. It's kind of it's a lot of technical apparatus involved. Right now, we're just working with the averages. And even with IV, we're only going to be working with the averages. But when Peter Hull has taught his instrumental variables class, he goes more advanced and he brings in the marginal treatment effects. It's just that, I only have a day, so I can't cover all of it. And it is an important area, but I leave it for Peter. But you have to use a propensity score. You have to use a propensity score to get it. Okay. Any other questions? Any other questions? Because we're going to do one more thing. If not, one sec. All right, I'm going to do this in real time. Okay, one question we're going to... Yeah, that's a way of putting it, Renz. That's definitely a way of putting it. A way of putting it. You can call it that. Endogeneity, though, has endogeneity is usually describing a regression model, I guess, because it's usually talking about the error term and how the treatment is independent of that error term. And it's, when you're talking that way, it it's actually a very pregnant kind of concept. But yes, selection bias would be a way to talk about endogeneity. Yes, without getting into a lot of details. That's right. Okay. So the second thing we had to do was we had to say, you know, what if you only have partial independence? Okay. So again, here was the full independence. Full was Y0, Y1, D. Okay. And with Y0, Y1, D, meaning treatment, assignment, whatever's determining it, it's not based on Y1 and Y0. So what that means is in the population, expectation Y0 D equal 1 equals expectation Y0 D equal 0. And let me give myself a little more room here. Expectation Y1 D equal 1 equals expectation Y1 D equal 0. All right. So we said, all right, with full independence, I can write down this. So then I go back to my SDO and I say, well, there's the average treatment effect plus expectation Y0 D equal 1 minus expectation D equal 0 plus 1 minus pi ATT minus ATU. And what we said was, notice right there, that's the same thing as this. So that goes away. And it's going to take me too long to write it down. But under full independence, what we showed yesterday is also when you have full independence, these four terms show up in here and this cancels out also. So under full independence, that also cancels out. So the reason we like, so notice, if full independence deletes both bias terms. Not modeling, not modeling the outcome. For example, fixed effects is a modeling of the selection bias. We're not doing that. We're not looking at the outcome. We're looking at the treatment. And we're saying if the treatment is independent of the potential outcomes, then it will not have selection bias. So it's not a modeling trick. It's like a real world property of the data. Okay. So now let's do this one. What about if treatment is assigned to units, but independent of Y0? Okay, so it's going to be people are getting into the treatment based on Y1. All right, so maybe it's like, you know, if Y1 is greater than some value, like maybe 5, D equals 1. And if Y1 less than 5, D equals 0, but Y0 never determines treatment. Okay. All right. So if that's the case, we write down this: Y0 independent of the treatment. And then that allows us to then write down expectation Y0 is the same for both groups. But not expectation Y1. See, so this we can use, but you know, that we can't do anything with. All right. So that we can't do anything with. So let's write down the SDO. SDO equals average treatment effect plus expectation Y0 D equal 1 minus expectation Y0 D equals 0 plus 1 minus pi ATT minus ATU. All right, so let's delete some stuff. That's going to go away. All right, that's going to go away. Why? Because expectation Y0 D equal 1 equals. That's what we were allowed to do. Independence with respect to Y0 allows us to write this down, which means that selection bias is 0. Okay, so I'm going to rewrite it. SDO equals ATE plus 1 minus pi ATT minus ATU. But we're not done because there are in here expectation Y0 terms are in there. There's an expectation Y0 term in here, and there's an expectation Y0 term in there. So we've got to deal with it. All right. So what we're going to do is we're going to write down the definition of the ATT expectation Y1 D equal 1 minus expectation Y0 D equal 1 and ATU expectation Y1 D equals 0 minus expectation Y0 D equals 0. All right. So we're going to basically what I'm going to do is I'm going to take this, I'm going to put it there, and I'm going to take this, and I'm going to put it there. Okay, I'm going to do that. Let me do that now. SDO equals ATE plus 1 minus pi ATT minus 1 minus pi ATU. Okay, so I'm going to go SDO equals ATE. Get that right there. Plus 1 minus pi expectation Y1 D equal 1 minus expectation Y0 D equal 1 minus 1 minus pi expectation Y1 D equals 0 minus expectation Y0 D equal 0. All right. So we got that. And that should be this. All right. So we got that. And now what we got to do is just kind of like group them together. So since this has got the same constant in front, I'll just write this down, ATE plus 1 minus pi times, you know what? It's easier probably to put it right here. So we're going to go plus 1 minus pi, okay, but big bracket, expectation, Y1, D equals 1, right? So that's this one, minus expectation, Y0, D equal 1, that's this one, minus expectation, Y1, D equal 0, that's this one, minus expectation, plus, that's the negative times the negative, plus expectation Y0 D equal 0. All right. Okay. So move some stuff around. Move some stuff around. Remember what we've got. Remember what we have up here. We can write, oops. We can only write this down. We can only write that down. So let's write that down. Recall. Y0 D expectation y0 d equal 1 equals expectation y0 d equals 0. So where is that? All right, let's see where that is. So here's this. Whoops. Okay, there it is. Where is that? Right there. There it is. And then where's this one? Y0 d equals 0. There it is. Okay, so look at that. That's a negative. That's a negative plus the same value. They're equal to the same thing. So that means I can rewrite it. SDO equals ATE plus 1 minus pi with only those two remaining. Expectation Y1 d equal 1 minus expectation Y1 d equal 0. And look what we have. It's like a different type of weighted selection bias. It's still biased. It's still biased, but it's a different source of the bias. It's a different source of the bias. Okay, let me read these questions. So let me read these questions here. Okay, so the questions were, Lygia says, do I need some assumption on the correlation between Y1 and Y0 for partial independence? Correlations do not technically, it doesn't go in that direction. So if you have partial independence, okay, then what it means, so no, you don't need anything. There's nothing like that. They don't have to be, you don't have to make any statement. It's all completely atheoretical. You could have independence with respect to one and not the other, doesn't matter. Okay, so you could have independence with respect to age and not have independence with respect to sex or with respect to wages. You're basically saying, I got it with respect to one thing, but I don't have it with respect to the other. And in the large population, the treatment will be independent of those two things because, like they're not like, it'll like kind of cut through that correlation. So let's see, since Y1 and Y0 are measured on the same outcome, they're not the same variable. Remember, they're not the same variable. They are completely different variables. One is your potential outcome in a world where treated. One is your potential outcome in a world where not treated. Okay? So you could write a simulation, actually. It might be helpful. Legia and MT, it might be helpful to literally write code. And in the code, you might do something like this. You might go, it's like you basically say gen y0 equals, 100 plus 10, right? You go 100 plus error. So basically say something like rand normal 0, 1. Then you say like gen y1 equals y0 plus 50. Gen delta equals y1 minus y0. And you might say like set observations, some giant number. Okay, some million observations. And then like, gen ID equal n. Okay, and then you would say like, all right, selection based on y0. You would say, let's see, gen d equal 0. Replace d equal 1 if y0 greater than equal to, be like 100. Let's make it bigger than that. Let's say it's like, 10. You got this big variance, and then you're going to go, all right, if Y0 is, so it's going to be, basically on average equal to 100. So let's just say if it's greater than or equal to 100, let's make it even bigger. So you're going to have like, if it's greater than or equal to 100, you're in the treatment. Otherwise, you're in the control group. Okay. And then you go switching equation. Well, actually, you don't have to do the switching equation. You can just go like, essentially, summarize Y0 if D equal 0, summarize Y1 if D equal 1, and then you can go summarize Y1 if D equal 1, D equal 0, summarize Y1 if D equal 1. You could like go through that whole thing and just check, check for independence with respect to Y0. Oh, that should be Y0. Okay. And then check for independence with respect to Y1. You could do that. Okay. And then you could even go like, check for independence with respect to treatment effects. You go summarize delta if D equals 0, summarize delta if D equal 1. And then you do the switching equation, G equals Y, D times Y1 plus 1 minus D times Y0. And, then you could just like go through it. You could do this kind of thing. You could check for selection based on Y1. You could do selection based on Y, you could do based on Y0, you could do based on Y1, you could go through the whole thing, you could do it based on delta. Whatever it's based on, you're just going to change that. You're going to change that. And then you could just check yourself and see it. Okay. Well, Y1 has let's do, I'll have to do it, Pappy. I need to do it probably. If Y1 is directly based on Y0, then yes. Actually, so you're right. So let's do it. Let's do it different. So it would have to be, it'd have to be like, you're right. So let's do like, 150 plus rand normal. Is that it? Rand normal 0, 15. Yeah, you're right. So here we have like two random variables. And so maybe this is what y'all were asking. Okay, so this is what y'all were asking. So if they are not independent of each other, then it would. Yeah, you're right. So, but this is the point. Okay, so now that's what I was realizing. All right, so in that example, though, if I can write it down, well, here, if I can write it down as one sec, Zoom iMac, it's doing this thing. If I'm able, so that's the point. Yes. Okay. So if I am able to write this down, okay, if I am able to write that down, this implies why you can have independence with respect to Y0, but not with respect to Y1. So there is this, independence of the two. So thank you. That's exactly right. I see now what y'all were saying. So yeah, that would be the case. And but if they're not independent of each other, so that was what, yeah. Thank you, Lygia. Thank you, MT. I see what you're saying now. Thank you, Pappy. Okay. Let me just real quick see what people are saying. When in application would that be useful? When would it be useful? Well, it's where I gave some examples yesterday. I said you could have person here, 3 forms. So you'd say, you chose the treatment because of what will happen if you don't. Okay. You chose the treatment because of what will happen if you do. You chose the treatment because the net benefits were positive. Those are all kind of like, broad examples of those are like broad examples of behavioral interpretations of selection. Okay. But what we're kind of saying here, what we're sort of saying is that if you are if you are if you are if you are willing, actually, I could even go a little bit further than I did. Yeah, there's actually a way to go a little bit further than the way I did, but it'll take me a little time. I just now realized that. But anyway, so well, all we're saying actually, MT, all we're saying is that there might be some way for you to be willing to make that assumption. Okay. There might be some willing because maybe you say, well, here's what we're saying, MT. Technically, all that I'm saying is that it's a weaker assumption. That's it. All that we're saying with this partial independence is that it's a weaker assumption. And in fact, without doing this, okay, so I this is going to take me I can do it over our break. So maybe that would be the way to do it. But let me show you where this ends up going. Okay, because I didn't finish. If we have here, all let me I want to write this down and not not just do it because I actually just thought of something that I want to try real quick. But let's take a 15-minute break so that I can kind of work through something because I want to answer something MT said, and then we'll go into this unconfoundedness work. But let me just real quick do some math, and then we'll come back on in a little bit. So we'll come back 3 minutes on the hour. Okay, so we'll be right back. MT, I'm going to work on answering your question in just a sec right now. So we've been doing some code, and I'm going to upload the code to the thing, but here's the code that we're doing. We're trying to illustrate selection on one or more particular potential outcomes. So here we have a million observations, and we generated Y0, we generated Y1. They're both independent. They're both they're both got these determinations. Okay. They're independent of each other. And uh and now what I'm gonna and then we've got a treatment assignment mechanism that's based on Y0. Right. So I'm gonna now calculate the average treatment effect, the ATT, and then I'm gonna calculate the ATU. I'm gonna do that here. Let's see what we get. Oh, shoot. Oh, no, I got to do it at the bottom here. Hold on. That was it. Yep. So, shoot. Egen STO equal mean Y if t equal 1 I'll do it like this. Y1 gen Y0 equal mean Y if D equals 0, gen STO equal Y1 minus Y0. All right. So if I do that, okay. Oh, shoot. All right. So there's our SDO. And let's remember we go SDO, ATE, ATU like that. Let's see if how they're similar. Oh yeah, I keep forgetting. I always forget this. So you have to go I'll call it here temp. Those of you that use R, it's all this stuff you have to do. Y1 equals min temp1. Egen Y0 equals min temp0. Because trust me, you just have to do that. So okay, look. Hold on 1 second. SDO equals 65. Average treatment effect equals 50. I feel like I'm doing something wrong. So selection based on Y0. Hold on. I got selection, but because Z, oh, yeah. So I have here SDO. Notice what's happening. The SDO is a bias estimate of the treatment effect, average treatment effect, but it's not a biased estimate of the ATU. But I need to real quick. So I can use the control group. I got to work through this a little bit. This is what I was wanting to do. So that was what I was wanting to do. That was what I was wanting to do. I want to work through that. But basically, what we're able to do is one of the things that's going to happen is when I have independence with respect to one of them, I can get one of the others. But over the break, I've got to just rewrite the math out. Sorry. So got to rewrite the math out. I wasn't really expecting it. Pi, I didn't calculate pi. I could have calculated pi if I want to do the full decomposition. Yeah. Yeah. That's right, Carter. I've got to write it up though. And I'm stuck in all these like pi terms. Mauricio, the what's going on here, Mauricio, is sorry, I'm not sharing my screen. So Mauricio says pi, where's pi? So the only reason pi matters is if you're wanting to do the full decomposition. But remember, the SDO is just going to equal a number. And then on the right-hand side, you've got the things that it could equal. And what's going to happen is what Jeff just said, which is when you have independence with respect to one or the other, it allows you to identify the conditional average treatment effects, not just the average. But I'm going to work on this a little bit because I sort of went on a tangent, and now I'm realizing this would be a good thing to work on. But let's go ahead and stop there. All right. So what we're going to do now is we're going to move into, oh, sorry. Let me do this. I apologize if I hope that wasn't confusing too much. I hope that was helpful to kind of go through all that, but I'm going to try to fix it over lunch because now I'm obsessed with it and just remind myself why it's collapsing to the ATU because I gotta write it down. So I'm stuck in my head. All right. Anyway, so that's kind of the logic a lot. So what we basically did was we just went through the logic of randomized experiments. Okay. And that right there would extend what we just did, would extend, this, the ability of independence to eliminate forms of selection bias and allow simple comparison in mean outcomes to reveal aggregate causal effects like the ATE, okay? Like the ATE. The ability of it to do that definitely happens in a controlled, randomized experiment, randomized control trial, okay? A/B tests, randomized control trials, lab experiments. Those things will identify average treatment effects without any real econometrics. Okay, you might do some things, but the simple difference in mean outcomes will, on average, equal the average treatment effect. There'll be some noise from working with a finite sample, but we're sort of working with the population level. All right, so that'll always do it. There are sometimes in the real world naturally occurring sources of randomization, okay? Or what my friend called, my friend Mark calls coin flips in the real world. It'll happen. It'll happen for all kinds of reasons. But when it happens in the real world, it typically is also happening at the same time as other things. Whereas in a controlled environment, those other things are not allowed to also happen. Okay. So what you have to do often in the real world is control for those other things happening and exploit the randomization that you think you have discovered. And I'll just give you one example. I'll give you one example of something I found in a recent paper. Okay. So in a recent paper of mine, I'll show it to you right now. So we just had this paper published, Journal of Human Resources, Cunningham, Clay, Seward, Vigliotti. Here it is. This paper just was accepted. It looks like it came out last year. Okay, published online. So they have a lag. No, it came out. It came out in the 58th issue. So, all right. So this was a paper called Adverse Impacts of Mental Health Needs on Jail Outcomes. Thanks, Jeff. Adverse impacts of mental health needs assessments on jail outcomes. It's the worst title. But anyway, evidence from transition age youth and adults. So here's what happened. If you look at my Vita, all right, if you look at my like research, my historical Vita, if you look at it, I basically studied internet mediated sex workers my entire career. So 2010, I get my first publication. 3 years after I got a job at Baylor, it was pretty brutal. I had a brutal tenure track experience and nearly got fired. So, and nearly got fired in 2010 because I didn't have a lot. So I have this like medical journal here that didn't count much. I get the BE Journal of Economic Analysis, sex work. I get a good a top field journal of urban economics, sex work. Then I get a chapter of my dissertation and I get something on meth. All right. So, but a lot of the stuff I start working on pretty much is meth and sex work. So then I do prostitution 3.0, calling it prostitution. You're not supposed to say that. But back then I did not fully understand that was not an appropriate language. Yeah, I know that's. So then I do meth. I don't do meth, but then I study meth, violent video games, meth. So I do 4 meth papers, but then I keep doing sex work. Sex work. I had some book chapters on sex work. I go sex work, sex work, sex work, sex work. And I edited a book for Oxford Press, but none of this stuff really starts to matter until recent. So then it's like sex work, random psychology journal on mental health. So I start kind of moving towards mental health at this point. Sex work, crime more generally, violence against women, abortion, sex work, depression. I'm kind of moving into mental health, random development study, sex work. Okay, so like most of the time, well, it wasn't really pharmaceuticals. It is pharmaceutical retail convenience. It was about meth. And one of the meth policies, well, the main policies that I always studied were precursor controls, Sudafed, and they began regulating Sudafed. So we did a contingent choice experiment on regulating access to Sudafed. And anyway, I did a lot of like sex work. Why did I say this? I said this for some reason. I switch into mental illness, and it kind of happened slowly. And in 2018, I kind of like really go all in. So even though this psychology paper was right here, I guess I don't even remember really why I got interested, but I like right here in this nature thing, I start being interested in severe mental illness and suicide in general. And then this paper right here is about suicide in the jails. So back in like 2018, I like start driving down to this big city and taking out government officials that work with mental illness in the jails. Actually, no, mental illness in the community, but they're like working with government. And I'm talking to, long story short, I learned that in this jail, I end up getting a gig with the jail. The jail gives me all the data, but I had to like work this for years, or not years, for about 6 months, but the project took me years. And so in the jail, there is a score that happens where they rate at arrest. So when they arrest a person, here's the way it works. You arrest a person, and then you take them to jail, and then you do the fingerprints. That's called booking. It's more than just fingerprints though, but it's like, you know, and that's usually what people, they got the thing where they take the photograph and they got the fingerprints, but they feel it's like a whole day. It's just tons of paperwork. And one of the pieces of paperwork is they have a clinician that will rate the severity of their mental health needs. And if you get a 0 or a 1, you're considered to be sort of, you know, you're doing fine. But if you get a 2 or a 3, you're not very functional. You might have schizophrenia, you might have severe bipolar disorder, so forth. All right. And so I asked the lady that I asked the people about this. I was like, well, you know, how are they getting this score? They go, well, the clinicians give them the score. Yeah, you did. They just came out, Chris. I'll show it to you. I go, well, how do they get the score? And they go, well, the clinician gives them to them. But then I thought, well, how are they getting the clinician? And the lady says, they're randomizing clinicians. At booking, they alphabetize every single day the therapists that they have, and then they just rotate through the therapists. Okay. So there was a source of randomization, potentially, of getting a mental health needs score if these therapists disagreed with each other, which they did. So these kinds of things happen. They happen. It's not just in a laboratory that you get a coin flip. Okay. You can get coin flips all the time, but these coin flips are not pure, is the problem. They're not pure. They're happening oftentimes in a context where you still can't do simple differences in means. I can't just compare people with high and low scores, because sometimes those high and low scores are because the people are mentally ill or not. And sometimes the high and low scores are because I got a clinician who typically gives high scores, and the clinician is being randomized. So what we have to now do is we have to kind of figure out, well, what methods have been created that kind of capture that coin flip, and allow it to be kind of targeted at the units. Because if you can find a way to leverage that coin flip, you can delete the selection bias. Not because you've modeled the selection bias, okay? It's not because you modeled it, but because you exploited the coin flip that was out there in the real world. And just because it's like that at that one jail does not mean it's like that at a different jail, okay? So what we're doing here is we are not leaning on in the design-based literature, you're not leaning on what you studied in your classes, okay? You're not leaning on what you studied in your classes. You're leaning on your in-depth understanding of your thing that you're studying. It's different. It's actually kind of empowering a little bit, because you might have studied education in your classes, but your study of education in your classes may not be relevant for the reason that people got into the charter schools in your city. Because maybe it's based on something in your city that's different from what it is in another city. Okay. So what you're trying to figure out, so there's a lot of listening involved. There's a lot of listening involved. There's a lot of skills involved with finding these coin flips. There's a lot of skill involved with finding these coin flips. Yeah, that's right. But sometimes the clinicians, sometimes the score itself, it's not exactly so. So Shuba asked a great question. Okay. You have to kind of be a little bit careful, Shubhangi. So let's say that it was a true coin flip. Okay. Heads, I'm going to say you're mentally ill. Tails, I'm going to say you're not mentally ill. Okay. That's what happens in the lab, right? In the lab, a coin flip determines the treatment. In the real world, it may not fully determine the treatment, because it could be the case that I got assigned a person who typically gives very high scores, okay? But, and maybe, for instance, like Miguel's like, Miguel typically thinks a lot of people are mentally ill, all right? So maybe that's the deal. It's like Miguel thinks people are mentally ill even when they're not. And Zoe typically thinks there's other explanations, and so she kind of under says it. But there's going to be situations where Zoe and Miguel both agree this guy clearly has schizophrenia. Okay, they're gonna definitely agree. So even though I got signed Zoe, who's like got a very low tendency to give that, okay, it's not the same thing as a true coin flip. So you got to kind of like find, there's methods that like harness and direct and isolate the pure randomization. And that's the issues. Like these naturally occurring randomizations, you still got to find methods that like eliminate the selection bias and then just target it. Yes, there are varying levels there. Okay, Pedro, so the rest of the class is basically about this, your question. We're going to go through each of them. 3, matching, or what's called unconfoundedness, which exploits a particular kind of that exploits randomization, but only in a particular way. Instrumental variables, which exploits a particular kind of randomization in a particular way. And then regression discontinuity design, which exploits a particular kind of randomization in a particular kind of way. They each are trying to do it in a particular way, and they're each only able to get a particular parameter for a particular population. So they're very limited There's different. So in some ways, Pedro, be thinking, everybody should just be kind of thinking of Pedro's question about this. Like, well, what is this method doing in order to harness and isolate that randomization? And what do I learn from it? Am I going to get the average treatment effect, or am I going to get it for a particular local population? Okay. That's exactly the thing. And so here for this study, okay, yes, there was a lot of econometrics involved in this study. There was instrumental variables, all right? But a lot of the work that went into the study actually was driving down there, cold calling lawyers and cold calling people that worked at the jails and taking them out for tacos and taking them out for Indian food. That was a huge part of the project. Taking them out for Indian food, taking them out for burritos and tacos and Tex-Mex, and just asking them about their job. Tell me again, why is it that people end up getting these scores? I don't really understand how they're getting the scores. They're never really, see, here's the thing. In the real world, the people that work for these government agencies or like for a school or whatever, they don't use language. They definitely do not use the words independence. And if you said the word independence to these people at a jail, they're going to be like, they're going to make up what they think it means. And if you ask them, is there any source of randomization in your data? They're going to say, who knows what they're going to say, but it's probably not right. You have to develop like a hearing, like a way a dog can hear a very high-pitched noise. You've got to develop hearing. They've got to say stuff. And when they say it, you go, wait a second, back up. Are you actually saying that they alphabetize the therapists? They're not assigning the really good therapists to the really schizophrenic people. Everybody's just getting alphabetized. There's no sorting. You don't say sorting. You just say, is that what you're saying? And they say, yeah. That's like, you've got to learn to hear the sources of randomization in the data. So Abby says, just to clarify, does it mean that in observational data, we try to look for sample design that creates randomization? Sort of. You are trying to say, if it's like this, Abby, in some observational data, in some observational data sets, it is not a pure Roy model that is determining treatment. Oftentimes, it will be based on something else. If that something else is there, there are methods that will allow you to exploit that randomization. Sometimes the selection is based on covariates, which is what we're about to do. Sometimes the selection is based on instruments, which is what we're about to do. And sometimes the selection is based on something called a running variable, which is what we're going to do with regression discontinuity design. 3 different forms of selection, 3 different classes of methodologies. Okay. But sometimes none of those work. And you can't use anything. And when you're doing that, well, you can't, there may not be in randomization. And when that's the case, you kind of have to go into modeling approaches, and not randomization approaches. So a lot of basically our class is all about the randomization approaches. But the diff and diff class and the synthetic control class, they're about modeling approaches. Diff and diff doesn't use any randomization. It uses something called parallel trends, which is a modeling of Y0. Synthetic control does not use randomization, nor does it use parallel trends. It uses factor models that are determining counterfactuals. Okay. But IV, matching, unconfoundedness, coin flips, regression discontinuity design, they all kind of have randomization. And as we saw yesterday, randomization is a gift that gives us the ability to delete selection bias. It's just each of the method has to exploit it in a different way. IV does not use covariates. Regression discontinuity design does not use covariates. Okay. Okay. So we got to get into the covariates. So what we're going to do is we're going to learn something called DAGs, directed acyclic graphs. And I only teach directed acyclic. People really love directed acyclic graphs. I mean, people lose their mind over them. They're great for teaching, but I'm going to kind of give some qualifications to it. I am only using the DAGs in the support of the design-based causal inference, but other fields other fields will computer science and machine learning areas and math and epidemiology, they use DAGs a lot more in a lot more sophisticated ways than I'm going to do it. Okay, so let's go ahead and close this down, and we're going to open up known observed confounders. So it's like here, causal inference 1, slides, this. Okay, that's what we're going to look at. And I'm going to spend 30 minutes on this. And then hopefully I can get through that, and then we'll hopefully make a dent in some of this. Do I use the DAGs? I use the DAGs for IV. I use the DAGs for IV. And I use the DAGs for instrumental variables because my brain really does think graphically. And if you see the DAG structure for instrumental variables, many of us, not all, but many of us look at it, and it can help you reason out where your problem areas might be. But I also use DAGs to teach unconfoundedness. And I don't really, I mean, I have published a paper that uses, like I do have this paper here, this one in the Journal of Development, and it uses propensity scores. So I have published on propensity using matching, and then this one's like a regression, and there's other stuff, but for the most part, I, don't always. So I think that if you're going to do regressions, here's the deal. If you're going to do regressions, if you're going to do IV, and you're going to put in controls or you're going to use an instrument, I think you have to have DAGs to think pretty carefully. Because if you just use your gut, it's going to probably be not credible. Okay. All right. So let's look at this. We're going to turn from potential outcomes modeling, causal effects, to causal graphs. Very old area, goes back to Sewell Wright in the early part of the 20th century. Ended up kind of, getting a resurgence under, I've used it. I have some co-authors that use it constantly. I would say that watching them use it, I'm probably not terribly enthusiastic about it. I'm not sold on a lot of this causal discovery stuff, but this is a very I will say this is a very active area. Miguel clearly knows about this area. It's a very active area, particularly in the tech industry, and in epidemiology. So it's a very important area. It's very common to see it in computer science, intersections with data science, particularly the tech industry. It's often very advanced. My focus is very narrow. I'm going to use it to teach design elements around matching and IV. So why do we do it? So one of the things I think people learn in a methods course, whether it's econometrics or statistics, is they learn the multivariate regression, right? And here's the multivariate regression. Multivariate regression is regress Y onto a constant plus, delta D, the variable of interest, plus beta X plus E, right? We just kind of call it controlling for X, right? It's like run a regression controlling for X. We say it so fast and so often, it's like, we kind of think we understand what that means, but many of us do not completely recommend, or do not, as we're going to kind of see, I think you're going to be surprised by what mathematically it's doing when you have heterogeneous treatment effects. Okay. Oh, I completely, Eduardo, that's what I'm saying. If you're controlling for variables, you got to use DEGs. If your solution is to address causal inference through controls, you got to have DEGs because there are such things as bad controls. Colliders, Eduardo, is what Eduardo just called it. And outside of the DAG literature, they'll just call it bad controls. But we got to figure out, what's a bad control and why is it bad? Okay. Oops. Okay. So, why do we pick covariates? What's their purpose exactly? And what should they be? And when you control for them, what causal parameter are you getting? Are you getting the average treatment effect? Are you getting the average treatment on the treated? Are you getting the average treated on the untreated? Okay. What are you getting? Right. So, I know what it was. I know what it was. Selection was based on Y0. So that meant Y1 was independent of D. And when Y1 was independent of D, yes. Okay. This was killing me. This was absolutely killing me. Okay. When treatment is independent of Y1, we can SDO equals ATU. See that? But what if selection is based on Y1? Then that means Y0, that's what it was. I got to show you. So here we do this one. I got to do the STO here. Let me show you this. If you can satisfy this right here, okay? And Y0 is independent of treatment. This is what I was wanting to show you. The STO will equal the ATT. Okay. So this was what I was trying to say earlier. If you can weaken the independence assumptions, you can still recover a causal effect. It just won't be the ATE. But if you're willing to say that the treatment is independent of Y0, STO will equal the ATT. And if you're willing to say that treatment is independent of Y1, STO will equal ATU, which is what we had up here. Up here somewhere. Okay, that's what I was trying to do. Sorry. I knew I was just going crazy. I could not stop thinking about it. It was the whole, because I'd never written out that equation before. So I'll show you in a second. All right, so here we go. Unconfoundedness is a phrase we're going to learn today. Selection on observables, phrase we're going to learn today. Ignorable treatment assignment, phrase we're going to learn today. Known and observed confounders, phrase we're going to learn today. Backdoor criterion, phrase we're going to learn today. They all basically mean practically they're the same thing. Okay. They basically mean that a randomized control trial, a coin flip, is taking place, but only conditional on the covariates. And I'll explain what that means. Only conditional on the covariates is the RCT happening. Okay, that's different than an instrument, and that's different than RD, and that's different from a laboratory coin flip. So we got to figure out, what does it mean that you have randomization, but only within the dimensions of a conditioning set of confounders and covariates. That's the purpose of today. All right. Purpose of today is to do that. So this is a guy named Yuta Pearl. Probably a lot of you know who he is and some of you don't. Yuta Pearl was the 2011 Turing Award winner, which is the computer science Nobel Prize, effectively. And he's the one that's kind of been the champion of he invented essentially directed acyclic graphs with him and his students and his colleagues in computer science, because he was in artificial intelligence back in like the early like the 80s or something. And in order to get this kind of reasoning to occur, or to now it kind of seems like we're nowhere close to it, to be honest, but he developed a kind of causal reasoning, and it was based on these graphs. And if you could write down these graphs, you could make logical deductions about causal effects and their magnitude, and then you could use estimation about their magnitudes. I cover in the mixtape DAGs. So I have here directed acyclic graphs, and the book was in working paper form, or it was a PDF on the internet. And Pearl said, "Why don't you come out to UCLA and I'll tell you everything that's wrong with the book." It's basically, he literally said that basically. So I was like, sure. So he'd never had an IPA beer, so we went out to dinner. That's his first one, and he let me take a picture of him. All right. So Yuta and his, it's called Yuta, apparently, not Judea. Yuta Pearl is what I was told. So Yuta Pearl and his colleagues in artificial intelligence at UCLA developed this DAG modeling to create a formalized causal inference framework. And it makes the causality concepts very clear. Some people find them extremely intuitive compared to the potential outcomes. All right. And they provide a map to the estimation strategy. And maybe best of all, they can communicate to others. They're extreme, so when you think about all that stuff I just went through, right? When you think back to when I was using my iPad and writing down all those potential outcomes, remember how I was making mistakes and stuff? It's like, and I was going page after page after page. All right. It's nothing like that with DAGs. DAGs are like, pictures, and they make the idea of causality so clear. That's why I teach them. That's why I use them to teach instrumental variables, which instrumental variables to students is oftentimes completely mysterious. They cannot really, undergraduates in particular, really struggle to understand what an instrument is. How is it different from a proxy? That's how I was when I first learned it. I just could not wrap my head around it. But when you see it in a graph, you're like, oh my gosh, that's what it is. That's easy. So makes the causality concepts very clear, provides a roadmap into the estimation strategy, and best of all, it's easy to communicate your strategy to someone else, and it's easy to interpret another person's projects. It's a lot easier to interpret their projects, okay? But here's the thing. They are very different than design. Design exploits randomization in the data, not a modeling of the data. DAGs are model-based approaches. DAGs require prior theory of the treatment assignment in the world, making it more structural than the design-oriented methods. The design-oriented methods are not modeling, a system of equations. They are very localized. They're very localized. The design elements are very localized. They're basically like, here is this weird source of randomization. It's only at booking. At booking, it only happens this way, etc. Okay? They go to, so they don't model how people get on Medicaid or model how people get on health insurance. They find in the data in the real world that some of the people are getting onto health insurance randomly. So it's very different. So it is the case that they are compatible, right? So they're not at odds with each other, but they're not really usually going to follow the same estimation strategies. They're extremely popular in epidemiology. I don't know the origin of that story, but they are. And they're extremely common in industry, and they're very common in artificial intelligence too. Causal Lens is an artificial intelligence firm that creates causal inference software. and they are all in on they're all in on DAGs. Are they used in economics? No, they are not. I presented a paper at the National Bureau of Economic Research that used DAGs, and I heard I was the first person in the history of economics to ever do that, which is not something to brag about because it's just viewed as, it is viewed by economists as just not appropriate. And that's part of the limitations of DAGs is that there's a lot of things that economists think about, like uh, simultaneous kind of determinationist stuff that DAGs, yeah, the Heckman has been has written with, I think, is it Pinto? Well, it is Pinto. Okay. So why are they not appropriate in economics? Well, people would disagree, Pedro, because people will do covariates or they will do IV, they are appropriate. But they're oftentimes the way that they're used in covariates and IV is really not, you're not really like using them to do some kind of elaborate strategy. They're like basically helping to justify certain parts of a design strategy. In economics, though, like for instance, if you're wanting to get the elasticity of demand, okay, you need to trace out prices along the demand curve and quantity, right? And to get that, you're going to need an instrument that shifts the supply curve. Anybody that would probably go about kind of modeling the whole process using a DAG, well, first of all, Heckman says it's not appropriate. He kind of has a whole paper about how it's not appropriate for simultaneity. Well, simultaneity is like a big part of economics. It's a big part of game theory. It's a big part of market equilibrium. So there's like a whole host of stuff that it's not appropriate for. Okay. Is that the Miguel, is that Heckman paper? Ah, that's the new one too, isn't it? Yeah, that's the new one. There actually is an older one, do calculus. Yeah. We make the case that economists who uncritically use either potential outcomes, they are discard or DAGs, they discard the benefits of the econometric causal model, which is to use economic theory to guide the analysis. So I mean, this is kind of the twin. This might be like the third approach, but Heckman's probably closer to this one than he is to this one. All right. Anyway, so but it's a modeling approach. DAGs are a modeling approach, and they kind of follow they're not necessarily economic theory. So my review of them is going to be basically to teach covariates. Here's some books for you to look at. This book is wildly popular. It's very general interest, came out in 2018. The Book of Why. It's very accessible. It's like the Freakonomics of DAGs. I mean, it's just like, people will read this book. Actually, this is what I've kind of noticed doing more consulting in tech. People will read that book and go start a consulting firm that does causal inference based on what they read about DAGs. I know two firms that did that. Causal Lens and Geminos both did that. They were just so radically impressed by DAGs, and they immediately saw how important causal inference was. And so, so that's the thing. So here's, that's one. Pearl, Glimmer, and Jewel is a very thin book that you could actually, it's almost like a textbook, but it's very accessible. This one is his magnum opus. It's very advanced and very difficult to read. And then this is Morgan and Winship, which has come up a few times. It's come up a few times. I think Jeff had said it. Wonderful, wonderful book. Counterfactuals, Causal Inference, Methods, and Principles for Social Research. I used to teach using this book. It's two sociologists. I have that one too. I think I have it here at the house. There's a few out there. So this book is written by two sociologists, and there's just something about them that they're very good at writing the. There you go. Zoe's up there throwing down the PDF of the Book of Why. All right, so here we go. The DAG, what is it? It is structural because it is supposed to be correctly describing a system of equations that determines the treatment, the outcome, all relevant routes between them. It's also called the structural model, but you shouldn't confuse it with structural econometrics, nor should you confuse it with Heckman's kinds of work, which structural econometrics literally brings in economic theory. Okay. So what's kind of going on here? I don't know that one. There's been a wave of books. There's been a bunch of them. So consider the following diagram. All right. Here's a DAG. Okay. It's a simple story about how in my data set, this is the determination of education. I got college determining wages, right? Maybe that's a 0. Maybe it's negative. Maybe it's positive. Okay. So I got this treatment effect. And then I got everywhere there's an arrow, it's a causal effect. Okay. Everywhere there's an arrow, it's a causal effect. So I've got family income determines whether you go to college, and family income, let's just say it also determines your wages for some reason. Okay. Parental education determines family income. Parental education determines your education, but parental education does not determine your wages, right? And then I've got some unobserved background factors. It's unobserved in the data. It can be real, but for whatever reason, it's not collected in the data, all right? So it's not in the data, but you know it's real, all right? And I say it's got a dashed line so you can tell the difference. So B, background, determines, not completely, but causes parental education, and background also causes you to go to college, all right? Okay, so this was invented by a geneticist named Sewell Wright. And so the language of all these arrows has all this like genetic language. So it's like, or heritability language. So you got like B. B is a parent of P, E, and D. P, E, and D here are descendants of B. Y is a descendant of B. Sometimes you'll hear somebody say D is a child of B. Y is a grandchild. But sometimes that's not as specific because Y is both a grandchild and a great-grandchild. Because look, Y is the child of I, is the child of parental education, is the child of B. So it kind of breaks down a little bit. The family language kind of breaks down a little bit. Yeah. So it's like I, family income. D, college. Y, earnings. B, unobserved in the data, background factors. Maybe it's like IQ. Okay. And then I got PE, parental education. Okay. Yeah. Where I'm from, there's definitely some stuff like that. All right. So B is a parent of PE and D. Okay. Yep. Could be effort, could be grit. It's some kind of unobserved latent factor, though. Okay. Some kind of unobserved latent factor. And so there's there's like these descendant stuff like that. And then there's like, you can also describe stuff in terms of graph theory. Yes, it could be. In fact, here's the thing, Chang. You're making a statement. You're making a pretty strong statement if you don't put an arrow there. Okay, you're making a pretty strong statement if you don't put an arrow there, because if there is no arrow there, all right, then you've said it doesn't cause it. Okay, but that's pretty strong. So you absolutely could have that. You could have that. But if you don't put an arrow there, then you have decided that background doesn't cause income except through parental education. And not only that, Cheng, but you also have this. Notice I said background factors don't cause income. They only cause education and parental education. Well, that's an assumption. Okay. So this DAG is filled with assumptions, both in terms of where the arrows are and the fact that there aren't arrows there. Okay. Based on whether or not you have all the variables you need and whether you don't. So you have here two also things here. You got D causes Y. If a variable has one arrow to another, it's called a direct path or a direct edge. It uses graph theory kind of language. But if you've got something like B causes D causes Y, yes, B does cause Y, but only through other variables, right? So look, you can get from B to Y, you can go B, P, E, I, through causal channels. You can go B, P, E, I, Y. You can go B, P, E, D, Y. You can go B, D, Y. Okay? So the causal paths all move in one direction, but technically any variable that is connected to another variable, that is a path. It just might not be a causal path. So like for instance, PE. I can get from PE through causal and non-causal channels. PE, I, Y. PE, I, D, Y. PE, D, Y. There's 3 causal paths, but I also have some non-causal. PE upstream, D, Y. PE, D, upstream, I, Y. So see how I can do that? I can go like this. Causal, 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 because arrows all move in the same direction. But I can also go non-causal. I can go non-causal. I can go non-causal. But you have to describe all of them. You have to describe all of them because they all imply certain kinds of relationships between the variables, and they're connected. They're connected in particular ways. I'll look at that, Mariko, in just a second. So DAGs are harder, though, than they seem. It's easy to write something down, but it's harder for it to be useful. It's harder for it to be true, okay? So DAGs are meant to represent the truth. Yeah, so B through Y. So yeah, that's a mediated path. B, D, Y. That's a mediated path because D is like a mediator, meaning yes, B is operating on Y, but only through another variable. All right, so B does cause Y, but not directly. Usually this is actually what we care about. This is actually what we care about because, you really want to know, like what like the further up you're getting, the less policy relevant it becomes because you're not really sure, if it's just kind of like operating on weird mediators or if it's like, it'll be causal, but it might not be very portable. But like something like this, where there is no mediator, then that might be always something you can carry with you. Structural equation modeling is what they'll call it. And structural equation model will have all these arrows, but it won't usually be causal. Reverse causality. There will be, so that's the other thing, Robinson. They're called acyclic. Acyclic means that there will not be any reverse causality. So you won't have this. And so you can imagine to the economists, they're like, well, that happens all the time. That's constantly happening. That's like a supply and demand curve. Okay. So I don't know, so that's the kind of stuff Heckman's like, there's so much in economics that if you have to rule out simultaneous equations and reverse causality, you've just cut out a bunch of stuff. But you know, insofar as you're using instrumental variables and insofar as you're trying to run regressions with covariates, then you're already not in those situations anyway. Okay. No, correct. Yeah, I think that's right. I think that's right, Sergio. They wouldn't be random. It would not be. Yeah, it would not be independent. That's right. That wouldn't satisfy independence. But that does not mean that you couldn't find an instrument that did. Okay. So they're meant to tell the truth. What determines the treatment in they're like theories of the treatment. So it's like Heckman's more of like the theory of the larger behavioral phenomenon. But DAGs are much more local. They're really about your data set and what determines treatment in your data set. It might be different somewhere else. Okay. So you have to be able to justify your choices. They have a complicated connection to the design methodologies because the design methodologies, like I said, they focus on randomization, not prior knowledge of system of equations per se. But you know, many design methods will require prior statements. So, you know, there is still like instruments will make prior statements that are untestable, and, you know, DAGs kind of allow you to make those statements. So your goal is in good faith to create a DAG that is a reasonable and an honest approximation of the treatment and the outcome, as well as direct and indirect effects of D on Y. So you're wanting to kind of, yeah, it's very tricky. It's very tricky. To solve reverse causality, you're going to need an instrument because even fixed effects won't do it. Because you got to break off one of the directions and not allow the other one to work. So, so in good faith is to create a DAG that's a reasonable and honest approximation. So that's what you're trying to do. You're trying to create a true DAG, not just simply justify, not just create a DAG that justifies the method that you want to do. Okay. So where there is uncertainty, you have to acknowledge that in the DAG. And where you have strong opinions, you got to acknowledge that too. You get the idea from theory, from models, from observation, experience, prior studies, intuition, conversation with domain experts. But keep in mind, these are not natural experiments. They are not exploiting randomized treatment assignment. Not necessarily, not exactly. And so you've got to be very cognizant, okay, of how lazy DAGs also can make you. When I used to teach DAGs a lot, I was really kind of frustrated because what ended up happening with my undergraduates was they could draw a DAG that always justified running a regression. They would be like, I'm gonna draw a DAG that basically allows me to really only use this one or two covariates. And I was like, wow, that's probably ridiculous, you know? So it's very easy to get lazy with the DAGs and you don't even know you're doing it because it's just so easy to do the building. So it's extremely common for it. And coming up with so the mathematicians and the computer scientists who developed the theory of DAGs are not necessarily the same people using the DAGs for estimation. They're two different groups of people. So nothing about DAGs is not true. Yeah, it's fitting a DAG around the treatment assignment. And the treatment assignment and your outcome is your data set. Correct. So so the practice of using it and the being the person who develops the theory, they're different people. Okay. All of DAGs are true. They're all correct and true, but the practice of using them is not the same thing. Okay. So when you're using DAGs, you're modeling the outcome. And if you're wrong, then the estimation is wrong. You know, if you found a coin flip, it's a different deal because we know what randomization does. Correct. Well, can I answer that question later, Mawson? I mean, it is true. Okay. But it's like, you're not really like going about it in the same way. Okay. You're not really going about it in the same way. but there is a sense in which all estimation is going to have to require some form of randomization, right? So, all right, so I'm about to be done with this part. So I'm not trying to turn you off of this stuff. I'm trying to impress upon you. It is a very different enterprise. And that's why I mainly use it for selecting covariates and justifying instruments, because those things themselves are very commonly done badly, and you need the DAGs. Um, kind, let's hold off, Zoe. You'll see what I mean in a minute. We're going to see that as it progresses. So that said, it's an extremely important area of causal inference. If you love this stuff, I highly encourage you to read more on it. But now we're going to look at the DAGs to justify the picking of covariates as controls. All right, so let's take a 15-minute break. We'll come back in 15 minutes and be right back, okay? Miguel asks, quick question about the Vimeo videos. Do you have permission to download them? I just gave you permission, so you can do that. Feedback is out. Yes, you can't have any kind of reverse causality with the DAGs. And so that's, so what you get though, Ronald, with the DAGs, that if you do want to model that, and I asked you about that myself, basically you have to kind of enforce it. You have to enforce. I went ahead and allowed it, Sebastian. I don't really care. So you have to enforce it as saying, well, variable treatment in 2024, outcome 2024, treatment 2025. So it's like, and to Pearl, that's like the way to do it. And I think a lot of people probably in economics kind of feel like that's going to be hard to defend a little bit, the modeling of that. So that's what you would probably do, is do something like that. All right, so what we're going to do is we're going to focus on the unconfoundedness assumption today, and probably a little bit of Saturday. And it's the unconfoundedness research design is just another way of describing controlling for covariates. So hold on. I just saw your comment, Miguel. So let's see. I think I heard you say before that some tools do not use it, but then so the stuff we're doing this week in this causal one can be thought of as the ones that use randomization. IV does. Regression discontinuity design can be thought of like that. And unconfoundedness does. Diff and diff doesn't. Synthetic control doesn't. Okay. So they all kind of belong in the family of the design, but technically they don't all use randomization. They don't all exploit randomization. These first three can be thought of like that. That's what I meant. Okay. So we're going to focus today on unconfoundedness, and within the causal graphs, it's a concept called the backdoor criterion, which you might not have ever heard before. So we're going to see what the main thing I want to really be emphasizing here is that we're going to be focused on situations where we don't have feedback effects. We do not have these simultaneous equations. So don't be thinking of it as like, you want to test your game theoretic model or your market model or something like that. So, or some kind of, duopoly, competition, strategic interaction between firms. But the thing is, you weren't going to study that anyway by just running regressions with covariates. You were usually going to take a structural approach to that anyway. So this is really about using it in the way that you've typically been running regressions with covariates, and this is all about picking the right covariates. There's the treatment effect. And now the treatment is also determining the outcome is also determining the treatment. So like an example would be in crime. Okay, Becker posited that more police will reduce crime. So that's D causes Y. But if police hire when crime rises, then Y causes D. That would be the feedback that Ronald was talking about. And so that's real. That's real. Okay. That's not saying that that's not real. That's saying you're not going to solve that by putting in control variables. That's what we're sort of saying. You're never going to solve that kind of thing by running regressions with controls. You're going to need to probably use an instrument that's increasing police for reasons that are not related to crime. Okay. And that's the way to sort of be thinking about it today. Okay. So we're going to talk about this backdoor criterion. All right. So there's this term most people are now familiar with called confounders. Confounders, what they do is they create differences in the treatment and in the potential outcomes. So what they do is they introduce selection bias. The selection bias that we were looking at yesterday, we really had no, this is kind of a comment that happened as we started out today. I don't remember who said it, but they were like, why would there be differences in potential outcomes for these two groups? Okay. Why would there be differences in potential outcomes for these two groups? And I was like, well, I don't know, but let's just assume that. But now what we're saying is like, well, maybe they have different covariate values. Okay. I have different levels of college because I went to a bad high school compared to you. And that bad high school also is having an impact on my wages. Right. So that's called a confounder. And the confounder can cause different levels of the treatment, differing values. And so it can create these, spurious correlations, because part of the correlation between D and Y might be causal. And part of the correlation in D and Y is that, well, X is changing. And when X changes, it causes D to change. And when X changes, it also causes Y to change. So, what we're sort of saying here is like, you would find, even if there was no, assume no arrow from D to Y, D and Y are still correlated for non-causal reasons. Confounders create correlations that between variables that, isn't a causal correlation. Okay. No, in this example, Eduardo, it causes both. You could have, yes, you could have that. You could have this right here, and you could have that. That's not a problem, though. That's not a confounder. So no, if it's a confounder, it's a parent of both of them. By definition, confounders are the parent of both treatment and outcome. Okay. So if it only does one of them, it's not a confounder. If it does both, it is. Okay. So what confounding does is so here's a new term. Here's a new term. It's called backdoor path. What confounding does on a graph, okay, now we're on a graph. On the graph, what it does is it creates a path from the treatment to the outcome that is not a causal channel, right? So that's a causal channel. That's a path. It's a direct causal path. This is a non-causal path. Okay, and that's one of these non-causal paths. And this one means that D and Y are correlated just because of that. So what you do with a DAG, you don't say control for. You say block. You got to block that backdoor path. That's the language they use. So blocking happens by setting. It's not mediators. It's always a parent situation, Jacob. It's not a mediator. So like a mediator would be this. X is not, or that would be, sorry. Brief. Okay. So that's not it. That's not a confounder. Confounders always have an arrow structure of being a child or being the parent. Sorry. The confounders are never a child of the treatment or the outcome. They're always a parent. There's a mediator. No, no, it's still going to be, so it'll still be so, because it's still the parent, or it's still the, it's still an ancestor. You can still get there. So like, the whole thing that makes it a confounder is if it's a non-collider on a backdoor path. I mean, to be honest, that's really what it means. So you can get to D from Y, you can get from D to Y directly through this mediator or through a confounder. That's a confound that, so that would be what it is. Okay. All right. So we can block. Our goal in the DAG is basically this. So we're going to let's write down the causal paths. Okay. D cause Y. Then we're going to write down backdoor paths. This is the way. So we're going to go, what are all the ways I can get from D to Y that is not a causal channel? There's that one. It's only one. It's the only one. If I deleted that one, there'd be no other way to get there. Okay. So you basically just look at it, you go, okay. So like, imagine that wasn't there. What's the only way you can get from D to Y? It's that way. Imagine that was there. You can't get there. Okay. So that's how you sort of find it. So what you're going to do, what you're going to do is you're going to try to close that backdoor path. You're going to try to block it. And you block it by looking to see if there are any confounders or non-colliders. There'll be a confounder. And I'll explain what a collider is in a second. But if you've got something on there where the arrows are pointing away from it, you want to try to control for it. So like when we say block, an example of blocking would be this: Y constant delta D plus beta X plus E. That would be an example of blocking. Control for. Okay, control for. All right. Okay, 1 second. I have a bad feeling about something in the kitchen. Okay. All right. So once we condition on X, or we block on it, what we can do is we can basically calculate these, but that's not the only way. That's not the only way. That's a regression model. There's another way we could do too. We could take weighted averages of STOs within each value of X. Like this. Let's say X was, say there was 50% of the sample had X equal 1, 50% of the sample had X equal 0. Blocking can be like this. 1, average Y for D equal 1 minus average Y for D equals 0 for X equal 1. So you would say, set it. We'll do it like this here. Okay, we'll just do, we'll do binary for now. 2 groups of people. There's only males and females in this sample. Okay, so we're going to do it for that, male. Okay, right? So what you did was you calculated 2 STOs, 1 per X value. Now you're going to take weighted average. This would be like the AT would be basically equal to 0.5 times first STO plus 0.5. We'll call it the male STO plus 0.5 times the female STO. And that'll give you the average treatment effect. We're going to learn more about it as the day goes on. But basically, what you're doing with blocking is you're setting the value of X to a particular number, calculating STOs within each one of them, and then combining them in a certain way. You can do that with a regression. You can do it like this. Okay. But all right. So when all backdoor paths from D to Y are blocked, then the only remaining path from D to Y is the causal path. Okay. And we call this satisfying the backdoor criterion. That whole thing is called satisfying the backdoor criterion, but you have probably called it, dealing with omitted variable bias. So when we run this one, okay, when we run that, so we had causal y, D, Y, and we had backdoor paths. Number one, we only had one, D, X, Y. That's the only backdoor path. So we now controlled for X, and that's equivalent to what this is. And what it's doing is with this regression, it's saying, well, find the variation in D within the values of X, take that average, and then the regression model will use of its own weighting scheme. It has a particular kind of weighting scheme that it does, but yeah, exactly. That's right. Jeff has exactly right. Under Angrist, he calls it the conditional independence assumption. That's what I call it in the book too. They all mean the same thing. So conditioning on X will satisfy the backdoor criterion with respect to a directed path if all the backdoor paths are closed, are blocked by X, and none of X is a collider. So we need to figure out what a collider is. So here's some examples, right? So here we want to know the effect of D on Y. It's always motivated by what the question is. So we want to know what's the effect of D on Y, and notice there are two different ways to get from D to Y. So you can go this way and you can go that way. There's 2 backdoor paths. So what we're going to do is we're going to close. Block on that one. We're going to block on that one. So let's write down backdoor paths. 1, D, X1, Y2, D, X2, Y. Neither one are controlled for. So this is currently open. This is open and harmful. Okay. And harmful. It's harmful because it's creating bias. Yep. Exactly. And then it weights them. The regression weights them. The regression chooses its own weights, but right now we're ignoring that. All right. So, backdoor paths, DX1, X2. So what we've got is it's harmful. So what we've got to do is to satisfy the backdoor criterion, we have to block on X1 and X2. Okay. That's what we're doing visually, but a regression might be something like this. And that's what that is. That is the execution of the backdoor criterion within a regression model, But we're going to look at a range of models, not just regression models that do it also. The purpose here, though, purpose here is for us to understand why these were chosen. These were chosen in order to eliminate. You don't need them. That's a great question. So let's say that we add error. We'll call it, we'll call it A. Okay. All right, let's go back to what we did. Backdoor paths. Number one, D, X1, Y. 2, D, X2, Y. Open. Open. What about A? You cannot get from D to Y through A. A causes Y. It is independent of D. So basically it's like Y constant D B1 X1 B2 X2 plus error, and the error E includes A. It includes A in there. It's in the error term. So if it's a singleton thing that causes the outcome but has no relationship to D, then it's not creating a problem for us. We don't need it. That we could put it in there, and if we put it in there, it's going to reduce our standard errors, but it's not needed for unbiasedness. It's not needed for unbiasedness. Here we have an unobservable. U. So let's write down all backdoor paths. Number one, D, X1, Y, open. D, X2, U, Y. And we're going to look at collider in just a second, Artie. For now, just make sure you understand these things. It's only harmful if it creates a path. It's only harmful if it creates a path. If you cannot get, so like right here, okay, A. So look, let's just do this. So we go this one, D causes that, go through here. All right. So once I delete it, it's like, it's not there. And then here's the second one. Let's imagine that one. So if that wasn't there, okay, then you're done. There is no other way to get from D to Y through A. Okay. So that's one of the ways you can do it. You can kind of like systematically delete each backdoor path just so you can tell if it's a problem. And you are only concerned about backdoor paths. You're not concerned about variables. You're concerned about backdoor paths. It's backdoor paths that create the problem. All right, so look, let's say, how are we going to close that backdoor path? We got to find a variable along it that does not have two arrows pointing at it, a non-collider. So I'll explain in just a second what already is a non-collider, but for now, none of these are colliders. Just assume that for now. So I go X1, control for it. Okay, I got to put that in the covariate. I got to put that in the control the regression. But now I've got this unobservable. Now I have this unobservable. So I've always learned that if I got an unobservable and it's a parent of the D and it's a parent of the Y, it should be a problem. But look, so long as you control for any variable along the path, any non-collider along the backdoor path, the whole path is shut down. You cannot get from D to U anymore because that's not changing. You can only move along the path if it's random variables. But once you set it to a particular value, it blocks it. So you can have an unobservable. Yeah. Yeah, exactly. Now it's in the error term. Now it's in the error term. It's still doing it. It's still, when it changes, causes Y, but it's when it changes, it's not changing D. Okay. So, okay. So the backdoor paths can remain open through two ways. Okay. When you're controlling for things in these strategies with controls, you can have an open backdoor path in two ways. Number one, you forgot to control for a confounder. So maybe you needed to control for a variable and you didn't control for it. So like it would be like this. Okay. In this example, maybe you ran this regression. Okay. When you do that, B will not equal the true beta. B hat estimated B will not equal the true causal effect, but it will here. When you run that regression, estimated B will equal true beta. Okay. So there's, so if you fail to control for the covariates that you need, if you fail to control for it, you'll end up with bias. No, the DAG, well, yes, there are methods. There are methods. On Tuesday, I'm interviewing Chris Tabor on my podcast. He has a paper, Altanji, Elder, and Tabor have a method for trying to check if you have unobservables. Emily Oster has a paper trying to check for, the degree to which you have a problem with unobservables. So there are papers like that. They're like kind of these sensitivity things. They require some assumptions, though. None of this stuff's a free lunch. So, like with the Altanji paper and Tabor paper, they had to make assumptions about the U's, and they were like, they do all these things and they check whether or not, the coefficient on this starts to do something. They'll look at various statistics. And so yes, there are. No, there won't, it won't be a problem. It will change the interpretation. It'll change the interpretation, Eduardo. It'll be a weighted average over both the direct edge and the indirect mediated effect. Okay, so there's one thing you can do. One way to have, if you're taking these like control for variable stuff, one thing is you could forget to control for a confounder. And if you forget to control for a confounder, it will be biased. Another thing that could happen is you could put in a bad control. So what is a bad control? A bad control is called a collider. When you control for a collider, it will introduce spurious biases. And this is the risk of just controlling for any of all variables in your data set. So let me show you what a collider is. So this is like, unfortunately, this is not the most pleasant example. And they have taken down this, it's no longer here. All right. But used to be here. There used to be a CNN.com headline where the actress Megan Fox, who was in Transformers, the robot movie in 2009, Megan Fox was voted worst and most attractive actress. 2009. I don't know what the survey was. It was probably something stupid. So anyway, someone could say that, beauty and talent in acting are negatively correlated. And they might say, the reason they might say, I have a data set. In fact, and in my data set, they're negatively correlated. Okay. But I want to give you an example. I'm going to give you an example of something. I want you to imagine that talent and beauty are actually not correlated. Right. So I'm going to show you what I mean. And we'll go here, documents, causal inference 1, lab, DAGs, and we'll go to movie star. All right. So here's our map. Look, beauty and talent are not correlated. And the reason why I know is because look, no correlation between them. I also just do that as the same thing. Yeah, well, I don't know why I did that. And then scatter, beauty, talent. They're not correlated. Okay. So assume that beauty and talent are both independent, and I did it by making them random draws from the normal distribution, a bell curve. You can sort of see it here. Okay. They're both like that, but they're not based on each other. But in order to become a movie star, you have to be really good at both of them. Okay. So what's the correlation between talent and beauty for a sample of movie stars? So here's what I'm going to do. I'm going to create a score. All the people in the data set go try out for a movie part, and the casting director scores their beauty. Okay. So it's like, this person's got a beauty of negative 0.6. This person's got a beauty of negative 0.9. She scores them and she gives them a score. So this person has a score of negative 1.59. She does that for 2,500 people. Okay, the average scores is a 0.018. Gets as high as a 4.3, gets as low as a negative 4.5. Okay. Then what she says is, well, anybody whose beauty and talent score, not beauty, but beauty plus talent, anybody whose score is in the 85th percentile, I'm going to make them a star. I'm going to make them a movie star. Okay. Now watch this. No correlation. Negatively correlated. Negatively correlated. Okay. So no topic. We're just kind of assuming we're just ignoring that. Just ignore it for now. Say this person has a rank ordering for it, and that's all it is. So look, okay, there is no correlation at all between beauty and talent, but in the subsample there is. So you might say, well, that's just like, the reason why there is because the only way you can be in the top 85th percentiles, you've either got to be like really beautiful, or you got to be really talented, or you have to be like combinations. And so you might say, yeah, Scott, we already knew that. That's about non-random samples. So look, 2,500 observations, zero correlation. Watch this. Star. 2,500 did not create a sample selection. Talent and beauty are negatively correlated. And look at and highly significant. Look at the confidence intervals. Highly statistically significant biased result. You cannot include a collider in a regression. If you include a collider in a regression, it will bias the treatment. It'll bias the treatment. It'll show spurious correlations that are not there. Collider bias, Jacob, will always occur if it's this DAG structure. Okay. It's this DAG structure. So you just have to think to yourself, is this DAG structure, is this selection variable here an outcome? Is it a collider? The way I was doing it was talent. Talent was the treatment. No. It's reg beauty talent. It's reg beauty talent. We're trying to say, is there a correlation between these two variables? Okay, is there a correlation between these two variables? There isn't, but when you condition on a collider, it introduces spurious ones. I don't know that, Malcolm. That if you can write down a DAG, okay, if you can write down a DAG, and then if you can write down the DAG, and you could make the equations, you can figure out if it is an example of that or not. I'm gonna give you another one. So notice it's not just sample selection, it's controls. It's controls, right? Let me give you another example, and then we're gonna take a break. Okay. It's very common for think tanks and journalists to say that the reason men and women make different incomes is because they work in different jobs. But if you control for jobs, men and women will make the same earnings. But what if the job is a collider? All right, so watch. Let me write all this down. F, female or male. D, discrimination. O, your occupation or job type. A, unobserved ability, grit, IQ. Y, earnings. Okay? Couple of things. Number one, distribution of F and A is independent. Notice that? So women, men and males and females have the same average ability and the same distribution of ability. So it's not the case that women or men are more likely to, there's not more high ability people, right? So that's modeled here. When F changes, A doesn't change. When A changes, F doesn't change. Okay. Number two, F does not directly cause earnings. That's what I'm trying to do right now. Trying to do it right now. Trying to give you an example of a collider, but you've got to write down colliders using the DAG structure. You have to write down the collider in a DAG structure. Okay. So here we have women are discriminated against. So what we're going to do is this. We're going to go, what is our causal question? All right. So let's say, assume you want to know DY. Okay. For whatever reason, what is the effect directly of discrimination on wages? That's DY. Okay. Now we're going to write alternative paths. Alternative paths. Not just the backdoor paths. We're going to look at all paths. Okay. Number one, how can you get from D to Y that is not this? What are all the ways you can get from D to Y that is not that? You can go discrimination, occupation, earnings. So what that means is, a woman doesn't get promoted, her earnings are less. Or a woman doesn't get tenured, her earnings are less. Or a woman doesn't get, as good a job, her earnings are less, whatever it is, but it's coming from the discrimination. So that's there. So it's not a backdoor path, but it's a path, and it's going to matter for what we're doing. So we're going to eliminate that one. Okay. Nope, that's not right. Sorry. Okay. So that's one path. It's gone. We have another path. D, discrimination. Occupation, ability, earnings. What does this one mean? So this one means, unobserved ability also gets you a good job and gets you higher earnings. This is like a classic selection. We cannot already, because that's what the dash is. For some reason, it's not in the data set. Okay. Now look, watch, Joy. So here we have, what we're going to do is we go, okay, I'm going to control for occupation. And when I control for occupation, that backdoor path right there is closed. Okay. But when I control for occupation, that right there is a collider. And the reason I know it's a collider, occupation is not a collider on that first path because it does not have two arrows pointing at it. But it is a collider in the second graph, the second path, because colliders have arrows pointing at it on backdoor paths from both sides. So you have to understand what a collider is. See, Joy, this is the thing. To understand what a collider is, you have to write down the DAG. You then have to write down the backdoor paths. You cannot trust your eyes. You cannot trust your eyes. You got to write and say, what are all the ways I can get from D to Y? Here, that's one way, and here. And when I go from here to here, and I block on O, I close that backdoor path, but I open that backdoor path. Because on that backdoor path, occupation is a collider. And the reason I know it's a collider is because ability is pointing at it and discrimination is pointing at it. Okay? Let's look at some code. All right. So we're going to make 10,000 observations. I'm going to make a random variable called female. You should not, Pedro, but I'm going to show you why. You absolutely should not, because it is a collider along this path. See, if you control for occupation, you've got two arrows pointing at it through that backdoor path, and you're creating spurious correlations. All right. So I've got female, some random variable, and I've got ability, also random. All right. Then I'm going to have discrimination being based on being a female. And then what I'm going to do is I'm going to have occupation. Occupation has two arrows pointing at it. Your job is based on whether you're discriminated against and how smart you are. Occupation based on Ability, positive. It's not based on whether you're female, but it is based on whether you're discriminated against. Yes, I think so. Jacob, it's this right here, when we control for occupation, because discrimination points at occupation and ability points for occupation. See, here's what's going on. D, O, A, Y. That is a collider. Okay. Alexa, stop. Okay. So, all right. So we have occupation, negative on discrimination, positive on ability. So I made that. And then we have wages. Wages, negative. We're going to just impose that you are being discriminated against. So it's going to be negative. That's the treatment effect. Positive on job. Better jobs get better pay. Positive. Smart people make more money. 2, positive. Okay. So we run wages against discrimination, and we get kind of like a combination of the discrimination effect, and we get a effect of the discrimination working its way through occupation. So you're going to get 2 things. But let's say that you controlled for occupation, right? So we know, look, here's the thing. We know that the coefficient is negative. Okay. We know that the coefficient is negative. We know that the treatment effect is negative. It's hardwired in the data generating process to be -1. When I run this regression, I get a -3. That's not correct. That's because it's like taking a weighted average over these 2 things. But what if I control for occupation? Okay. Occupation's right there. Positive. It reversed the sign. When I put in a bad control, in this case, it introduced more bias. It dealt with it. When I put in occupation, I got rid of the mediator path, but now I opened up a backdoor path from discrimination through ability. And since ability has a really big effect on the wage, it's, not putting in that collider, it's creating a lot of problems. The only way that I can get an unbiased estimate of that is to control for discrimination, occupation, and ability. And then it'll be correct. -1, -1. But the whole problem is you don't have ability. We can't, Becky. So what this is saying is that we do not have the ability with this data set to satisfy the backdoor criterion. Okay, that's all it's saying. Paths. Number 1, D, O, Y, open. 2, D, O. It's actually closed right now. Colliders, when you leave them alone, always close that backdoor path. Okay, so right now it's closed. But the only way I can close that path is to, the only way I can do it is to control for O. But, once you control for O in one place, you control for it everywhere. And so now all of a sudden, that's closed, but that's now open. And so you just introduced bias because you controlled for a collider. So all this is to say, colliders can be outcomes. Okay, colliders can be outcomes. You don't want to control for X2, or they can even be pre-treatment characteristics. Here's a situation. There's this unobserved U. They both control X. Paths. 1, D, U2, X, U1, Y. Okay. So if you control for X, you have put in a collider. Okay. So all this is to say, you have to let theory all right, I'm gonna quit here. So, some people, what they do is they just control for all the omitted, they just put everything they can put in there. They put in every variable they can put in, as many as possible, and they don't really think about the treatment assignment mechanism. They have no idea what variables are colliders, covariates, empty covariates that don't matter, or confounders. And machine learning can be naive. Double debiased machine learning, causal forests, all these kinds of things are like handling lots of covariates, but they can be naive. If you include unknowingly colliders in there, it can create bias. So double machine learning, automated model selection by Paul Hunderman, Byers-Lau, Ito Caspi. This is a paper that came out just recently. Double machine learning has become an increasingly popular tool for automated variable selection in high dimensional settings when you have like 5,000 covariates. Even though the ability to deal with a large number of potential covariates can render the selection on observables assumption more plausible, there is at the same time a growing risk that you are controlling for endogenous variables, which would lead to the violation of conditional independence, which is what Jeff called it. This paper demonstrates that double debiased machine learning is very sensitive to the inclusion of only a few bad controls in the covariate space. The resulting bias varies with the nature of the theoretical model, which raises concerns about the feasibility of selecting covariates in a data-driven way. All I'm saying here is that you've got to pick covariates that are going to eliminate those backdoor paths. But what if you really don't know? I'm almost done. Probably RENs. I mean, the point here is, so if you have the DAG, that's the best case scenario. If you don't have the DAG, here's what you want to do. Include any confounders that you are pretty sure about. Okay? Any confounders that you are pretty sure about. Yeah, Miguel Hernan has written a lot on this. Put those in. Include any covariates that are highly predictive of any missing counterfactual. Well, you're going to be in trouble, Pedro. This is what I'm saying. Covariate selection without DAGs, that's what this is right here. That's what this is. Number one, if you can't do the full DAG, but you are worried about something being a confounder, put the confounders that you do know about in there. Okay? Avoid anything that can be considered an outcome. Don't put in there anything that's post-treatment. Don't put in post-treatment values of the characteristics. Okay? Put in, if anything, pre-treatment. Does not guarantee it, but probably it's safer. It's probably safer. And then include covariates that are highly predictive of whatever the missing counterfactual it is that you're trying to estimate. But don't just put in everything, because you could put in a bad control. So there's various falsification tests that you could do. Covariates shouldn't be affected by the treatment, for instance. So examining them as falsifications are recommended. So, running a regression of the covariates against the treatment, that might be a way of making sure that it's not a collider. Imbens and Rubin suggest using the pre-treatment outcomes as a way of checking. They should have similar confounding structures. Okay. Falsifications are also there. I'm going to skip that. Okay, so we're going to take a break. Nita, we're going to take a break. I'm going to think about your question. We went over about 10 minutes. We'll come back in an hour and we'll finish this. I'm going to let you guys, I'm going to read these and then I'll get back to you in a little bit. Okay, so we'll come back in just a minute, in an hour, and then we'll get into unconfoundedness, and I'll be answering these questions over the break. Nita, you said, how do you model something like women's lower likelihood to negotiate salary offers? That is up to you. Probably you could have F go directly to earnings. Might be one way to do it. It's just going to depend on exactly what you think is going on. If you think there's some, some reason they do that, then it might be a confounder possibly. But if you don't think it's a confounder and you just say it's like it's an attribute or something, then you would just probably draw a direct arrow. The way that we did it, we were just like, assume that none of that's going on. Okay. Let me look at these comments here. Len has an interesting looking paper. I'm gonna have to pull this up. I'm gonna look at it later. Okay, so Sergio, I left an answer for you. Lygia says, what's a closed path really mean? Even occupation is in the path. Okay. Question was, what does a closed path really mean? Closed path means that right now, if I ran this regression, Y, constant, D, so it's like, okay, beta D plus gamma O plus error. All right. If I ran it, there would be inside beta hat some weighted combination of dy causal d o y mediated path, right? It would not include this. The parameters that link D and Y here would not be like propagating through this relationship between the two variables. But if I did this, Y constant plus beta D plus gamma O plus, psi. Oh, sorry. No, my bad. Do like that. Okay. So if I did that one right there and only regressed Y onto D, I'd get the direct effect and I'd get the mediated effect because part of the way that D operates on Y through that mediated effect. Okay. But I would not get this one because it's blocked because O is stopping that particular relationship. But if I ran this one, there would be inside beta hat, some weighted combination of D causes Y, causal, D O A Y opened collider path. And you'll get a very different coefficient. So the point here is to say, well, what is it really doing? What it's saying is that you could do a decomposition on this, I mean, theoretically, and you'd be able to talk about this new collider path as like a different version of selection bias. Is there a simplification? Nah, Artie, there's not exactly. There's tests that you can do. So there are like implied in a DAG because so in that DAG, no. In that DAG, there's no way to do it. The DAG structure will imply that certain variables are independent of each other. There's ways to try to evaluate whether your DAG is consistent with the data. That is possible. It won't say what each variable is, but it'll say, the DAG that you've written down implies that certain variables are unrelated to each other. Maybe they're blocked by colliders, maybe whatever. And then you can then test that. So there are things like that where the DAG structure will imply that there'll be no relationship between certain variables if you specify it a certain way, and that's testable. Okay. But it still doesn't tell you like that's a collider. It just says, here's an example of a DAG. It makes these predictions. I'll test these predictions. I can't reject. But that's not the same thing as saying that's the only DAG that's possible. There could be 500 DAGs. I mean, I don't know how many. There could be more than one DAG that kind of is consistent with the data. So there's a limit to the ability to really do that. It's always two arrows. Okay. It is always two arrows pointing at the variable on a backdoor path. On a backdoor path. That's why I was saying everybody that does this, they have to write down all the backdoor paths. It's not just looking at the graph and finding two things pointing at it. It's basically write down D, write down Y. What are all the ways to get from D to Y that are not the causal question? If you see there might be 5 paths. And if you look down those paths, and you see anywhere where there is a variable on that path where two arrows are pointing at it, it's a collider, and you don't have to worry about that path. If you control for that variable, it will open up it'll open up a spurious correlation. The size of it really depends on how big these various magnitudes are. See, so we have like a really big, we have this like really big effect of ability on wage. And we have this occupation has a big effect, ability has a big effect on occupation. That's why when we ran this regression, the sign flipped. If we had done didn't do it. Okay. So it's like, it really depends on how big those structural parameters are. But the whole problem is you don't know what they are. So, I mean, a lot of this is like, it requires a decent amount of information to be able to say things. So you're wanting to know, what's the question, Mauricio? You're trying to figure out the effect of D on Y? You're not going to be able. Okay, well, on this first one, you block that. Backdoors. D, X2, Y. Open because X2 is non-collider. So we need to close it, and I just closed it. Then that's the only one. Well, then you could do all these other things. You could go D, X2, X1, Y. I think that's the only one. And that's open because X2 and X1 are non-colliders. But if you control for X2, then you've satisfied the backdoor criterion. So you only have to go row by row. You only have to go row by row to deal with it. So we'll go like control for X2, you control for X2, that's closed, that's closed. That's not a, you didn't condition on a collider, you didn't collision on a collider. So there you have, it's straightforward as long as, but you have to write it down is the point. You have to write this all down and then just go one at a time. There is software that'll do it. So yeah, well, no, it's not. It's not a collider because a collider is not, Eduardo, a collider is not an attribute of the variable. Okay. It's not an attribute of the variable. It's not like race or something like that. Colliders is an attribute of the path. Okay. It's an attribute of the path. And look, there's X1. X1 only appears on one. Well, okay. Okay. I see. Hold on. I see what you did. Yeah, it is. You're right. My bad. I didn't see that one. D, X1, X2, Y. All right, perfect. So you want to control for X2. Okay, so you want to control for X2, but not X1. If you control for X2, then this is now closed. This is now closed. And that right there, already closed. Already closed because X1 is collider. See, it's a collider because D is pointing to it. X2 is pointing to it. Don't control for it. I mean, it wouldn't really matter if you did control for it, that's already blocked. But if you controlled for it, there'd be, D and Y would be completely independent of each other. So that wouldn't solve anything. So if you're trying to just get the causal effect, the best you can do in this DAG to get a causal effect is get the effect of D on Y mediated through X1. I think. I don't see, unless there's, well, wait a second. You might be able to do the front door criterion. I can't remember the front door criterion, but you might. Well, I think that's screwing up the front door criterion. I have to think about it. You might be able to get the front door criterion by getting, yeah, I'll look at it. I think that this might satisfy the front door criterion, but I used to teach it. Now I don't teach it anymore. But it depends. If you're, oh, yeah. If that's the treatment, then there's a front door criterion. But I got to remember. It's on my notes. It's in my old notes. I can't remember. But yeah, I'll look that up. So that particular DAG might be the front door criterion, and I can't remember. But I think what I just said is true, is that you'll get the overall effect of D on Y. You just might be able to do more, but I can't remember if the treatment has to be there or there. Anyway, D is no related to Y, just via X1. Okay. All right. So I'm not 100% positive about if you can get more than that. I can't remember, but let me tell us where we are. Okay. So here's to summarize what we did. All right. Everything about that we did was just about saying, be careful about putting in colliders. Okay. The goal is to satisfy the backdoor criterion. And if you do not feel as though you have enough information, okay, you should be very cautious about using a research design that really is depending on covariates. The less you are able to be confident that you are controlling for the correct variables, the less willing you should be to use simple regressions. Okay. And anything that uses covariates. All right, so here we go. I see you typing, Merritt, and I'm gonna type. I know that, probably everybody's wanting to spend more time on them. We'll do some more in just a second, but that's kind of the fundamentals of DAGs for this exercise. All right. Now we're going to just go into the actual estimation method using potential outcomes as our motivation of the sources of the bias and the techniques we can use to eliminate that bias. Okay. So we're going to talk about a non-experimental study, and you think that you need to control for variables. Which one? So we're going to look at the sinking of the Titanic ship. All right. So let's say that, so the Titanic sunk on its maiden voyage, early 20th century, cold water, 700 people died, or 700 people lived, and like 1,500 died. And it was supposed to be the opposite of that. A lot of people didn't get on the lifeboats, and there wasn't enough lifeboats and so forth. So it sank. Okay. But there was like different levels of the ship. All right. There were different levels to the ship. There was like a top level that was first class. And then there were like levels deeper in the boat, deeper in the ship. It went first, second, third class. And then there was the crew. Okay. And let's say that you wanted to know what was the causal effect of being seated in first class on surviving the sinking. Okay. What was the effect of being seated in first class on surviving the sinking of, surviving the sinking of the ship? Well, here's the deal. This is one thing that you should know about the Titanic, which was the captain, which was common at the time. There was a maritime rule that if you were a woman or a child, okay, you were supposed to get on the boat first. And then all remaining people were supposed to get on after all the women and children got on the boats. Okay. So I'm going to draw this DAG. Right. You know that women and children get on the boat first. But the question is, do women and you know that women and children get on the boat first. Sorry, no, that's not the boat. That's first class. Right. So that's first class. You know that women and children get on boats first, and that makes them survive. But if you're in a boat, you're going to survive. Okay. Question is, do women and children, are they more likely to be in first class? Or is first class completely independent of those characteristics? Because if there's different levels of women and children in first class, since you know that women and children are more likely to survive, when you just compare first class to non-first class, it'll always be biased. All right. So we're going to write down all the paths from D to Y, both the direct ones and the indirect ones, the backdoor paths. So here we go. Here's the question. D's effect on Y. It's the direct edge representing a causal effect with associated causal parameters like the AT, ATT, etc. All right. Okay. We can get from D to Y going that way. Okay, we did. Okay, you can go DWY, you can go DCY. So we're going to put that down as backdoor paths, and we're going to remove them. So we blocked on women, and now you can't get from D to Y through women. And then we're going to block on children, and now you can't get from D to Y through children. Right? So this is what in an old paper by Jim Heckman, him and his co-author called a known and quantified confounder. Okay. Here's what it means. A variable like C is a known and quantified confounder. Yeah, you can. That's what a collider does. Colliders are variables that take you against the direction. Yeah. Confounders Confounder, that's what confounders are. Confounders go again, they got you go start here D. How do you get from D to Y? You go up, down. So the arrow is pointing to D. Oh, the arrow is pointing to D from C and C to Y. C to D, C to Y. So that'll be like, this is like that kind of triangle structure where the variable is the parent of the two, of the treatment and the outcome. That's a confounder. That's a confounder. But when the variable is the child of the treatment and the outcome, that's a collider. Okay. So a variable C is a known and quantified confounder if the researcher believes it's a parent of the treatment and it's a parent of the outcome. Okay. Confounders must be known and they have to be in your data set correctly measured. That's the two things. You have to know that it's there. You have to know that it's a confounder ahead of time, and you have to have the data on it so that you can block on it. Known, quantified. You could know it's there and it not be in the data set, and it is known and not quantified. And you could not know it's there and it could be in the data set, but it's not going to help you then because it's unknown and quantified. Okay. So confounders may or may not be observed, but they must be known if they are confounders, because confounders create those backdoor paths. We use the solid lines, means they're quantified. The dashed lines, not quantified, not in the data. And the backdoor criterion is only appropriate for known and quantified confounders. If either known or quantified is missing, then what we're doing today is not going to be useful. So here's the deal. If you have ever run a regression and put in control variables, you have been assuming that you knew you needed it and it was measured correctly. So everything we're doing the rest of the day assumes that you knew this DAG. Okay? All right. What if we have one more variable? All right. So I got D. I've blocked on W and C. Right. So let's just like write down our paths. Here's our causal. Here's our causal. D, Y. Okay. Here's our non-causal. D, W, Y. Open, non-collider, need to block. D, C, Y. It's open, non-collider, need to block. What about B? D, B, Y. Closed, collider. Do not block on this variable. It will introduce collider bias. What about X? You cannot get from D to Y through X. So you can control for it, but you don't need to. The only thing that controlling for it will do is if X explains Y by a lot. If it explains Y, if it has a lot of explanatory power, meaning it's highly correlated with Y. If it is, the only thing is if X explains Y a lot, then including it in the model will reduce your standard errors on D. It's the only thing it's going to do. So you could do this. You could go Y. You do that, you get delta hat equals D equals, equals delta. All right, so you do that. Now you can do this. If you do this, you get BX delta hat will still equal delta. You'll get the same number, but the standard error will be smaller because X explains a lot of the variation in Y. It reduces the residual variance in it, and it'll increase your precision. Yeah. So putting in controls. Yeah. Okay. So the backdoor criterion means that the backdoor criterion just means that these variables are necessary and sufficient to identify that treatment effect. Okay. That's all it means. Backdoor criterion means there is no way to get from D to Y except through the causal path. Can't get there because that's a collider. Can't get there through X because it's not connected. Can't get through W because you blocked. Can't get through C because you blocked. So the only correlation left between D and Y is the causal effect. You're just going to have to come up with an estimator that will allow you to get that parameter of interest. That's it. Okay. Okay. So I call it a covariate. I'm not going to do that. So, all right. So I have a Substack you can read. Which variables do I need to control for? I've got this whole thing, but you can also read this paper by Carlos Sinelli, Forney, and Yuta Pearl in the Journal of Sociological Methods and Research. It's in our readings. It's called A Crash Course in Good and Bad Controls. What are you saying, Anthony? In the second non-causal, I don't think it should be C. You have to. See? It's a confounder. So you have to control for it. You have to control for it because D, you can get from D to Y through C. You have to close it. That's why you close it. Does that make sense? Exactly. Yeah. We have to do both. Look, we have to do both of them. We have to control for W. We have to control for C. That's all we need to control for. We can put in X if you want to. It'll increase the precision of the estimate of D on Y, but it won't change the bias. The bias is already eliminated. Now, if you control for that, that Carlos Sinelli and them talk about that kind of situation, Lynn, and that will reduce. That's like that'll reduce. It ends up reducing the variation in the treatment. See, can I say you can say that confounders create backdoor paths. They are not the backdoor path. They are a variable on a backdoor path. All right, let's get into some estimation. So step one is if you're going to be estimating causal effects using covariates, okay, remember, step one is always define the parameter. Which parameter are you going to try to estimate? Is it the average treatment effect, average treat on the treated, average treat on the untreated? It's the only ones we've talked about so far. Covariate adjustment strategies can get any of those. They can get any of them. The assumptions, though, are different for each of them. All right. So covariate adjustment strategies like regression or matching can identify them, but in non-experimental data, they will not be equal to one another if the treatment differs for people and you've got selection on, these variables. So it's upfront. You've got to decide what is your research question in terms of a population. So when you define the target parameter, defining the target parameter is simply another way of saying which units in my data set am I estimating causal effects for. If it's everyone, that's the ATE. If it's just treated group, that's the ATT. If it's just control group, that's ATU. Okay? And the purpose right now is not to say which of those are better. That's not the point. The point is to say you have to decide which one you're going to go get. All right? That's what you're trying to say. You have to decide up front, do you want the average treatment effect or the average treatment on the treated? Because not all methods can get the average treatment effect. Diff and diff cannot get the average treatment effect. Instrumental variables cannot get the average treatment effect. So you've got to decide up front, what is it that you're wanting to know? All right. Okay. So here's the first thing. Remember, okay, ATE. Let's say the ATT. No, it's not. The intent to treat is also called the reduced form. It's basically the effect of the, it's kind of like the effect of the instrument almost on the outcome. It's basically like, you've been exposed to the treatment, but I don't know if you actually took it up. So, like, well, it can be, Miguel, now that I think about it, I see what you're asking. It can be. It largely has to do with the fact that, like, I flip a coin and heads, you're going to have to, heads, you're going to have to exercise, and tails, you're going to have to diet. Okay. I flip the coin, but I actually never know if you exercised, and I never know, if you did diet. I know you were assigned to it, but yeah, you can't. So you can get the intent to treat. Yes, you can always get the intent to treat. If you're missing the treatment status, but the instrument status, that'll be the ITT. You won't technically know the effect for the people that were actually on it. And sometimes you can't know it. Okay. So, all right. So we'll write down the ATT. Expectation, Y1 minus Y0, D equal 1, equal expectation, Y1, D equal 1, minus expectation, Y0, D equal 1. Okay. So here, we're missing that, right? So if I was to obtain an unbiased estimate of the ATT using any method, and the ATT is equal to that expression, then it follows I have somehow not just estimated the ATT, I must have also estimated the missing counterfactual. Okay? Because the ATT is based on the missing counterfactual. So it must be somehow that's right. That's right, Sheree. So it must be that if you have correctly estimated that, that data you have, so somehow you must have estimated that. Sometimes the techniques do it. Sometimes the techniques literally estimate this, and sometimes they do it kind of implicitly. So like synthetic control, Synthetic control literally estimates it. You can see it. All right. Other times it'll be like automatic and it won't actually, it'll be like, it'll skip the step. So regression does not have two steps. It doesn't calculate that and then take a difference. Okay. It just simply goes directly for it. But behind the scenes, it's sort of handling this, in a particular way. Okay. So this is what Embens and Rubin said. They said at some level, all methods for causal inference can be viewed as imputation methods. It's just that some are more explicit than others. So all causal inference is about imputing missing counterfactuals. It's just sometimes like synthetic control, it's, it's very, very clear that's what it did. And sometimes with regression or inverse probability weighting, it's not really as obvious that it was like imputing. Okay. But they always are. So if you are wanting to estimate aggregate causal parameters, all right, let's think back to the randomized experiment. With the randomized experiment, with randomization, to estimate average causal effects, you only needed independence. With these covariate strategies, but not regression. With these covariate strategies, you need a version of independence called conditional independence or unconfoundedness, and you need something called common support. It's easier to explain common support if you see it. Regressions don't need common support, but we're going to get to later why it is. It's not really, they have other things that they need. So let's look at that. So we're going to focus on unconfoundedness is what I'm going to be calling it. Unconfoundedness means that there are no more confounders. After you've included the covariates in the model, there are no confounders and you didn't include a collider. Okay, that's what it means. Everything we are going to assume, though, is that you are satisfying unconfoundedness. All right, so the rest of the day assumes that you wrote down the correct DAG, and in the data set that you have, you can satisfy the backdoor criterion, which in this potential outcomes framework means that there are no longer any confounders. You're controlling for them. Okay. It's controversial. Unconfoundedness is kind of controversial because it basically is going to be assuming that, even though people are not flipping coins when they go to college, they're not flipping coins. For people with the identical covariate values, they were flipping coins. I'll explain it now. So here's what unconfoundedness means. There exists, so this will be all the variables you controlled for, women, children. So there exists a set X of known and quantified confounders such that after you adjust for them, treatment is random. Okay, so it's like for people with the exact same values of X, treatment has nothing to do with Y0, Y1, right? That's what it means. For a large group of people within the same strata of X, it states that those people, same race, age, education, etc., those people with the identical values of X chose the treatment randomly. So it says there's still randomness in the data. It's just randomness within the dimensions of the covariates. Okay. If you've eliminated all the backdoor paths, that means you did it. That means you believe that it is possible that you found randomization in the data. If it is the case that you can satisfy unconfoundedness, you're going to be able to write down those equalities. Average Y0 for the treatment group equals average Y0 for the control group for people that have the same values of X. You'll be able to write that down. So it's just like we did before. Remember when we had independence? Independence said The average value of Y0 is the same for the two groups. The average value of Y1, same for the two groups. What this says is average Y0 is the same for the two groups for people that are observationally the same. Okay. So let's say it's like, let's say that it's X is, let's see, lowercase x is male. If you have unconfoundedness, you would say Y0 treatment group men equals Y0 control group men. Then you do this. So it implies these equalities, but it doesn't imply this one. So it's only within the X's that the equalities hold, not if you don't control for the X's. Okay. And the reason why that's valuable is that for the same thing we did before, what we're going to be able to do is if we are missing this variable right here, Y0 for the treatment group, we can just use Y0 for the control group. Because it's going to be the same thing, so long as we have the same X's in both groups. Okay. All right. So here's like a visual. I tried to get ChatGPT to help me with this. So here's what common support means. Unconfoundedness. Just think of unconfoundedness. Like this is like a castle. Unconfoundedness means you have an army that can go across. Okay. Common support means there's a bridge. That's what it means. It means that there are X's on both sides. All right. So if you want to know, like, if you're wanting to know if it's X, that means if this is holding, then we're set. We need men in both groups. We need women in both groups. That's what this means. Okay. If you only have men in one group, but not the other, you can satisfy unconfoundedness, but there's like no bridge. There's no bridge. The bridge is what allows the troops to go across. Over common support is like the bridge. So if you're going to use these methods, you got to have X's on both sides. So common support says for ranges of X, there's a positive probability of being both in the treatment group and the control group. Okay. And if you say dimension, K dimensions, it means basically every single combination of the conditioning set. So when we said women and children, it would say women and children, if they're both dummy variables, male, female, adult, child. Dimensions means all possible combinations. No, common support is not the same as balance. Common support means that there is a non-zero probability of being in the treatment group and the control group if you're a man. So it's got to be a probability between 0 and 1. Okay, it can't be all the men are in the treatment group. Is that the same as balance? Balance says that the means are the same. Yeah, maybe maybe that's the same as the balance table. That could be right. I hadn't thought of that. Yeah, I think you're right. I think you're right, Eduardo. So dimension though means every combination. So we're not saying that there's men in both groups and women in both groups. It means there are old men in both groups. There's adult males in both groups. There's adult females in both groups. There's young males, young females. That's what it means. That's what it means. It means all possible interactions are distributed in both groups. Well, okay. So sorry, that's what it is. My bad. And okay, Eduardo, it does not require that the means be the same. I'm sorry. Yes, no, it does not require covariate balance. It does not require that they be distributed equally. It requires that there is a positive probability of being both treated and not treated, not that they have the same distribution. Thank you. Thank you, Anna. That was exactly, I knew that wasn't, so I had this big lunch, and for some reason I don't feel tired, but I feel like I ate too much. Okay. But here's the thing. Common support is observable. You can see if you have units in both treatment and control. You can see it, okay? But if the dimensions of X is really large, it won't hold, okay? So if it's like, here it's really simple. We have two dummy variables. With two dummy variables being what we're conditioning on, there were 4 possible stratifications to the data. So if we're going to do that blocking thing, and we're going to take differences in means within each of those groups, then, you got to have young females in both groups. But if you were to get like, 3 races, then you're like, all of this for whites, all of this for black, all of this for Asian. The more stuff you add in, the bigger this starts to get, the bigger the dimensions start getting, and it starts to blow up. So if you have like a continuous covariate, you actually cannot satisfy common support because, yeah, that's right, Jeff. If that makes sense to you, that's exactly right. There is no empty cell. We're going to look at empty cells in just a second. Okay. You can, technically, Jeff, you can always fix these things. That's called coarsening. You can coarsen a lot of this, but technically speaking, the assumption is kind of like if there's any heterogeneity, like within that coarsened variable, okay, then you've kind of like assigned units that are very different. So technically, unconfoundedness is not based on a coarsening. Unconfoundedness is based on the dimensions of X. That's technically what the assumption is, which is for those dimensions of X, 4 people with those identical values, it's a coin flip. But your data set could be too small. And if your data set's too small, you might not you might satisfy unconfoundedness because it's just coin flips, but that doesn't mean that you have all the covariates on both sides. It could be like, you got 10 values of observations and there might be 15 dimensions to the data. It's literally impossible. Okay. So you're trying to compare groups of individuals who have the same values of X. Okay. And if you satisfy this strong unconfoundedness or that full independence, you're basically saying conditional on X, treatment is independent of gains. Okay. And then this is the representation of common support. Basically means the probability of being in the treatment group is never 0 and it's never 1. It's above 0, less than 1. Technically, Lynn, it's still, the propensity score still kind of assumes common support at the base level. If you do not have that exactly, you'll have bias. You need both of these. And if you're missing this one, there may be some bias. It's going to depend on how big the treatment effects are and how they differ. But all that the propensity score is going to do is collapse all the X's into one X. It's a dimension reducing. And, if you have common support, then you don't have to match on the X's. You can match on you can match on the propensity score. But technically speaking, you still have to have, at the root, units with the identical K dimensions in both groups. The propensity score won't fix that problem. It just summarizes them into one thing, allows you to work with that one variable. Okay. All right, let's take a little break. We'll come back in 15 minutes, and we'll keep going. Let's take a little break. have it right there. So yeah, he's fairly, does not think they're super valuable. Much of the work in economics is closer in spirit to the potential outcomes perspective. Look at that. You know who that guy is? That's yours truly. All right. So hold on. Okay. So estimating average treatment effect with assumptions. Okay. With assumptions. Um, all I want to do, I don't know if this is helpful, but I want to show you something. Sometimes it's helpful to do this um, just to see it written out, I think. So let's just write this out. Okay. So you can see what we're doing. I don't want to do it, at length like I did this morning, but let me just sort of show you what I'm wanting to help you see what it is that unconfoundedness is actually doing for us. Okay. So here, it takes a little bit of time to do the mirror. All right. So, okay. So here we have, here's independence. Okay. Y0 D. As a result, you can then write down Y0 D equal 1 equals expectation Y0 D equal 0. That's what independence does for you. It gives you permission to write that down versus unconfoundedness, or as Jeff said, conditional independence. That's what I call it in the book, but I've been more and more likened to call it that. So watch, here's conditional independence. Y0, still independent of D, but only for the same values of X. You would go expectation, Y0, D, D equal 1, X equal X equals expectation Y0, D equals 0, X equal X. Okay. So what we're able to do here is even though that right there is, counterfactual, if there's ever a point where we need it, then we can use this instead. So if we have the need for this, okay, then we can just use this one instead. So like, what would be an example? When would I ever need expectation Y0 to equal 1? Okay, when would I ever need it? Well, the ATT. ATT is expectation Y0 to equal 1, 1 minus expectation Y0 to equal 1. Well, that's missing. So we don't have it, right? So that's the problem, is we don't have that. But what do we have? We have this. We have that. So all we got to do is just substitute that in there because it's equal to the same thing, but we've got to do it now on the X's. That's fine. That right there, we don't have to do anything with that. That one we can use. It's this that we have to use. Expectation Y0 D equal 0, X equal X. We can estimate the ATT even without expectation Y0 D equal 1, because unconfoundedness gives us permission to replace expectation y0 d equal 1 with expectation y0 d equals 0, x equal x, because they're the same. They're the same under unconfoundedness. But all that unconfoundedness lets you do, is it gives you permission. It gives you permission to replace common support. Common support isn't about permission. Common support is about whether it's possible to find the matches in the data. That's what common support is about. Common support is about whether or not it's possible to do the replacing, not whether or not you have permission. So you need both. You need both or it's not going to work. All right. So here is expectation y1 for the x. All right. That's the average treatment effect. And here would be okay. Unconfoundedness lets you use y0 from the control group as y0 for the treatment group. And it lets you use y1 from the treatment group as the control group's y1. It lets you replace them. And as a result of that replacing, all that you're doing is you're letting x be the guide. You're letting x be the guide. And then common support basically says the x's are in both sides. That's all that it is. It says the x's are there to allow you to do the replacing. It's all about that. Once you're doing the replacing, it's with the X. I was wondering that as I was writing it. All of a sudden I kind of blanked out. But yeah, you've got to match the units in the treatment group with their X's with the control group units. You've got to do the X to X. I should have wrote that down better. So sometimes you maybe want the average treatment on the treated. You might not want the average treatment effect. If you want the average treatment on the treated, you've got to assume that y0 is the one that's random with respect to D conditional on X. And whatever is over here that's independent, that will be the things that you can write out those equalities. That'll be the ways that you can do replacements. Okay. Okay. All right. So let's get going. So let's look at some estimators. All right, let's go look at some estimators. We're going to build it out around 3 different kinds of exact matching, inexact. Oh, yeah. Right. Okay, so we're going to do exact matching. We're going to do inexact matching. We're going to do regressions. Okay, we're going to do those 3 things. And inside inexact matching will be propensity scores. So we're going to go a particular kind of matching that we're going to do. Inexact match. I don't know. I shouldn't call it inexact match. I should call it exact matching weighting. Yeah. Okay. I'll show you what I'm about to do. Okay. I'm going to do something called subclassification. I'm going to do exact matching. I'm going to do inexact matching. I'm going to do weighting. And then we're going to do regression. So it's going to be 5 things. Subclassification, which you probably haven't heard of. Exact matching, which you could probably imagine what it is, but you haven't maybe used it. It's rare that you could do it. And then the inexact things gets back to what Lynn was saying, which is, well, sometimes we don't have all the dimensions there, but we could summarize them in a particular way. And maybe that would allow us to do it. So we'll be looking at that with this inexact part. Okay. The themes that we're going to be looking at are heterogeneous treatment effects, common support, correct and incorrect regression specifications. Those are the three things we're going to be trying to hit. Okay. All right. So let's look at subclassification. It's an old method. Well, here's the history of covariates, actually. Yule uses multivariate regression in the 19th century to study essentially welfare programs, cash transfer programs for the poor. And I think he's looking at work, something like that. So he's looking at, like, if you give people, he's running regressions, late 19th century. It's pretty incredible. And Ronald Fisher's doing it too. Okay. 20th century. So there's uses of multivariate regression 100 years ago, 140, years ago, whatever. And then there is a method that gets adopted because for a long time, causal inference was just with experiments. It was just with experiments. In econometrics, there was all these systems of equations, but it was just with the experiments a little bit. There was instruments too, but outside of that stuff, it went like this. Statistics, it went like this. Then it was a method developed by Cochrane in the late 60s to study smoking. It's called subclassification. Then in the early 80s, there's a method called propensity score matching by Paul Rosenbaum and Don Rubin, very influential paper at Biometrica. Then in the 50s and in the early 70s, there's another regression-based method that ends up being called regression adjustment that we're going to look at. And then there is machine learning methods like double debiased machine learning by Victor Chernyshkov, Causal Forest, Susan Athey, Stefan Wager, and then there's probably some other stuff I can't think of right now. But then there's the various versions of nearest neighbor matching that aren't propensity score matching. Okay, so what is this subclassification method? All right, so let's stick with our Titanic. All right, so Titanic sinks April 15th, hits an iceberg. 2,200 people are on board. Only 700 survived. 20 lifeboats, 60 capacity. It could have saved 1,200, and only 700. It was tragic. Women and children first. And what we want to know is not just a graph. We want to know what's the causal effect of first class on survival, adjusting for WNC. Okay. All right. So we did this. Here is the method called subclassification. What you're going to do is it's a 4-step procedure. Now, there's no standard errors with this. So, there's other methods that you might need to do to get, you could maybe bootstrap or something, but I'm not going to do the inference. I'm not going to create something. You could probably bootstrap. So yeah, you could do that. So, all right. So Titanic exercise. Here you go. Step 1, stratify. Stratify. What does that mean? Well, I got 2 confounders. I have to look at all possible combinations, write them out. So you're either male, female in this example. In the data set, you're either male, female, or you're adult child. So that means you have 4 strata. 4 strata. Male children, female children, male adults, female adults. Then calculate the differences in survival rates for male children in first class and not in first class, female children, first class, not in first class, male adults, first class, not in first class, female adults, first class, not in first class. You can sort of see that common support, right? You can sort of see that common support because I have to take survival rates for this group in treatment and control. I got to do it. So if I don't have any female children in first class, I can't do this part. I can't calculate the differences, right? Then once I have all of the differences in those, this is basically SDOs, but it's SDOs within, there's 4 SDOs, 1 for each dimension of the covariate set, then calculate probability weights. It's going to be easier to just show you that mathematically. Then once you've got differences in means and you've got probability weights, you just add, you take a weighted average of all these. You add all of these together, you take male children multiplied by its probability weight plus female children differences multiplied and so on, and then you get you can get an aggregate causal parameter. So we're going to look at all the ones you can get. So let's look at the typical, this is like your typical balance table. This is what you would probably see in a paper. You'd go, here's your treatment group, here's your control group. Let's look at each individual covariate, okay? Percent adult, 98% of first class are adults, 94.5% are adults in the other classes, 44% are female in first class, but only 17% are female in the other classes. All right. Now that's not stratifying. This is stratifying. This is a stratified balance, or this is stratified on the outcome. This is stratified. Yeah. Stratified on the outcome. No. This would be, yeah. So here is the stratification on the outcome. All right. So we go male adult, 33%, 32.6% of male adults in first class survived. 18.8% of male adults in the control group survived. Okay. Female adult, 97% of the female adults in first class survived. You can see that big women and children first thing going on, right? Women in first class, about 3 times more likely to survive than the males, or than the females are, than the males are, okay? And then over here, 62% of the female adults in the control group survive, 18.8. So still a much larger group, 3 times as many survive, okay? Male children, all the male children survived. In the comparison group, sadly, only 40% survived. In the first class, all the female children survived, but there was only one female child in first class. Only 5 male children in first class, and all of them survived. In the control group, only 61% of the female children survived. Okay? So we have all the data that we need right now. First step, stratification. We did that. Second step, calculate differences within strata. So let's look at how we're going to do it. Step 2, calculate differences in mean outcomes, survival rates within each strata. Male adult. Average survival for first class minus average survival for non-first class. That's going to be 0.326 minus 0.188. .138. So if you are a male adult seated, if you are a male adult, 13.8 percentage point increase in survival rates for first class compared to not. Okay. We do that for all of them. Let me write it out. 1.138. Okay. So on the next slide, I'll have all of it. There it is. 0.138. 0.972 minus 0.626. That should be 0.346, 0.346, and so on. That's where all these numbers are. 1 minus 0.407, it should be like 0.59 something. 1 minus 0.613, it should be about 0.3 something, right? That's what those are. So we have done step 2. You'd be surprised, to be honest, how this simple method is being used over and over and over again to this day in different contexts. Okay. So it's not as out there as it might seem. So then we have to calculate probability weights. All right. And this right here, this calculating of the probability weights is how you're able to get different causal parameters. Exactly. We don't use it yet. We don't use it. We're going to use these differences in mean outcomes for every single causal parameter, right? So let's look at, say that you want, okay, we want the ATE. We need two things. Number one, for the ATE, we need differences in means within strata. And number two, we need probability of being in each strata. So for instance, male adult probability weight, 1,667 out of 2,201. 0.75 something, 0.757. So the probability of being probability of being a male adult is how many male adults are there? What's the total sample? Okay. Sergio, we lose common support. We're going to do that in a minute. Okay. So let's go through. There it is. All right. So for average treatment effect, okay. So to summarize, for ATE, probability weights are total number strata, total number sample. And then you do it by strata, and those will sum to 1. Then to get the ATE, it would be P1 SDO1 plus P2 SDO2 plus P3 SDO3 plus P4 SDO4, which will be 0.76 times 0.138 plus 0.19 star 0.346 plus 0.03 times 0.593 plus 0.02 times 0.387. Should be 0.19615, 0.19615 rounded. Okay. So that's how you get the probability weights for the average treatment effect. For the average treatment effect, it's total number of people in a strata as a share of the total, period. But what about for this one? Okay. So for that one, for the ATT probability weights are number of people in first class per strata divided by number of people in first class. It's only about that, this one. ATT is just going to be, the ATT weights are just going to be about, ATT weights are just going to be about this. Okay. Whereas the ATU weights are going to be about this column of observations. And then the ATE weights are going to be about this. Okay. They're going to be about that, but it's always within the strata. All right. So let's go here. 0.175. What's the probability? Oops, sorry. 175 out of 325. There's a 0.5. There's a 53.8% chance if you are in first class that you are a male adult. 0.538. There it is. What about the next one? 144, 325 should be a 0.44. 0.44. Okay. So there's the weights. ATT weights are This divided by this for that one. This divided by this for that strata. 5 divided by 325 for that strata. 1 divided by 325 for that strata. Okay. And then the last one is this: 1492, 1876 for the ATU. The weight on male adults is going to be 0.795 and all the way down 0.8, rounds up. Okay, so we get different weights. This is the thing. We can get any causal parameter. We just weight the SDOs differently based on which population we are trying to study. No, it's not that, Julietta. It's not that. It's not probability of being in first class. It's in first class. What's the probability of being an adult, male adult? There's 175 male adults in first class. There's 325 people in first class. So if I take a random person from first class, there's a 175 out of 325, probability that they're an adult male, or 0.54. There's a 54% chance you are an adult male if you are in first class. That's how you interpret it. Does that make sense? Yep. Perfect. All right. So then what we do, look, let's do this one. Let's say we want that, okay, let's assume I am interested in the ATT. So here's what I do. 0.138 times 0.5, 54. 54 plus 0.346 times 0.44 plus 0.593 times, now look, see, that's a big survival rate, but it's shrinking it. It's making it kind of small. 0.387 times 0.00 something. There it is. That's the estimate of the ATT versus the SDO. I must have done it here. Let's look at it. Let's look at it together. Okay. So if we go here, right? So I'm gonna do this here. Stratify the confounders. Right. So here's the data: class, age, sex, survived. Okay. Step 1, stratify the data. Step 2, calculate differences within strata. I use this long thing to do it. Okay, so I have the average survival for adult females, first class, average survival for adult females not in first class. Then I label it. Okay, so I do that. I do it for all of them. Step 3, calculate the probability weights. Got to do it for ATE. Got to do it for ATT. Got to do it for ATU. Okay, so I go through. Oops. Here's all of those weights right there. ATU. ATT weights. Adult male, 0.54. Adult male, 0.54. See, there they are. Okay, and then we've got estimate the aggregate parameters. Okay, estimate the aggregate parameters. Here they are. So I got ATE, stratification, 0.195, 0.23, 0.19, there it is. There they all are. What's this SDO? Here's the SDO. Some survived if first class equal 1. 62% of people in first class survived. Some survived if first class equal 0. 0.27 survived that weren't in first class. So what's the difference? There's a 35 percentage point increase in survival rates if you're in first class versus not in first class. But once you stratify, it almost cuts it in half. But these are now only measuring the first class effect. These are only estimating the first class effect. Yeah. Probably, Jeff. I think it might be that, what exactly is causing the first class effect? Is it that they're closer? Is it wealth? It's not really, all we know is that it's not women and children. We've eliminated the women and children because we're only comparing people that are comparable on observables. Right. And this is the non-parametric version of selection on observables. So we were able, and so this question just came up. Yeah, for sure. For sure. Sergio says, what would have happened if there were no female children? All right. So I drop a child. I drop a female child from first class, Sergio. Okay. Now watch. For male adults, I can take average survival, both groups. Female adults, average survival, both groups. Male children, average survival, both groups. Female children cannot calculate a mean survival rate because there were no female children. This is called no overlap or violation of common support. Okay. It may be the case that unconfoundedness holds and I don't have a probability of being in first class per strata that is above 0 and below 1 per strata, right? So right now, if you are a female child, there is 100% chance that you are in all the other classes. And there is a 0 probability that you are in first class. But for all the others, male child, there is a 5 out of 64 probability of being in first class, which is neither 1 nor 0. For female adults, there's 144 out of 425 probability of being in first class. So common support by whether or not I have observations in both groups, not balance, observations in both groups. It just has to do with their existence. And the reason is because we can't calculate the difference in means and we can't calculate the probability weights. All right. So look. So I won't be able, female child, I can get those 3 survival rates. Just look at this real quick. I can get each of those survival rates per those. Can't get this one. Okay. I can get for the average treatment effect weights, I can get that one, that one, that one. Can't get that one. And by definition, the average treatment effect is weight plus that times that plus weight times that plus weight times that plus weight times that. So I can't get the average treatment effect because I don't know, anything about I don't have any female children in first class. Estimates. Estimates, Joy. See, we don't know the real ATT. We can only estimate the ATT under unconfoundedness and common support. If those two assumptions are true, then we can use this subclassification method and obtain an unbiased estimate of the ATT. But remember, estimates are not the same thing as the truth. Okay? We don't know what each person in first class survival rate would have been had they been in the control, not in first class, had they not been in first class. ATT is always, expectation survival first class minus expectation survival not first class, right? But so we can't know that because, for first class, for the people in first class. Oh, right. So this is survival if 1. This is survival if 0. So ATT is for the people that are in first class. Okay. What would their survival be if they were in first class, which is, that's, we know that information already. And then this right here is for the people in first class, which would be Kate Winslet from Titanic. Kate Winslet was in first class. What would have been her chances of survival had she not been in first class? So, I don't know this one. I never know it. What we're doing is we're estimating it using this stratification method. Okay? Does that make sense? You have to keep separate the target from your estimation of the target. Okay? You got to keep them separate. Good. All right. So, average treatment effect is a weighted average over all 4 of them. That one's missing, so we can't get it. Average treated on the untreated is weighted average. We have all the weights. See, we can get, actually, if you look back, we can get all these probability weights. It's 1492 divided by 1876, 281 divided by that, 59 divided by that, 44 divided by that. So it's possible to get every weight, but we can never get that differences in means. So you can't, you can't get the, actually that weight does exist. That weight does exist right there. That should be 44 over 2200. I have to change that. But so it's got to be weight times this plus weight times this plus weight times this plus weight times this. Okay. But for the treatment group, where are the treatment group? We only have 3 strata for the treatment group. See, for the control group, we have 4 strata. For the average treatment effect, we have 4 strata. But for the treatment group, we only have 3, which means that for the treatment group, female children are irrelevant because there are no female children in the treatment group. So that means that for the units in the treatment group, we just need common support for them. And we do have that. We do have that. We have somebody in both groups. For everybody that's in a treatment group strata, we got somebody over here. We don't have any female children, but that's irrelevant. That's irrelevant for this parameter because this is our treatment group. So we only have to look over here. So this gets thrown out. We don't even use this. We don't even use it. So you can get the ATT. You can get the ATT, but it's the only one you can get. Under unconfoundedness, you can. Under unconfoundedness, you can trust it. And common support's not violated. Common support is not violated for the ATT. For the ATT, you need two things. Number one, Y0, D conditional on X, right? Unconfoundedness. It's kind of like a weak unconfoundedness, all right? It's like a weak. And then number two, there is at least one person in the control group for every person in the treatment group per strata. Okay, so that's what you mean by 0, probability D equal 1, X 1. Cannot be all of the strata observations are only in the treatment group. But it does mean we can't say anything about the female children, but since there aren't any in the treatment group, female children are irrelevant for the ATT. They matter for the ATE and the ATU, just not the ATT. Okay? We do count the strata of the male children. We do. Okay? We do. Male children, 5 out of 324. So there, the male children have a probability weight of 0.015. There it is. 0.02. There's the 0.015. So it's 0.015 times male children, 0.0. Yeah, so it's, there it is. 0.015 times this. So we do look at the male children because since there are male children in the treatment group, we need common support for male children. Since there are male adults in the treatment group, we need common support for male adults. Since there are female adults in the treatment group, we need common support for female adults. There are no female children in the treatment group, so we don't care about the female children are not a part of the ATT because they're not in the treatment group. So they don't matter for that parameter. They matter for the other parameters, just not that parameter. Does that make sense? Great. But you can see where this is going, right? How easy it is. We add in just like a couple more variables, right? You add in just a couple more variables. Race. Say there's 3 races. Now all of a sudden, there are 12 dimensions to the data. Male adult white, female adult white, male child white, female child white, male adult African-American, female adult African-American, so on. Male adult Asian, female adult Asian, all the way down. So now we're at 12. The more variables that you get, it's not just 3 variables. Since you're stratifying, every variable is like causing the dimensions to sort of go, I don't know if it's going up, what it means to go up exponentially, but each new variable is doing way more than just adding one dimension. Each new variable is like adding in as much as 12, as much as 8. Here we added in a variable with 3 values. It added in 8 new strata. If we had done income and income is continuous, well, then you can't stratify. How are you going to do it? Male adults who make $12.57 There's not going to be any male adults making $15 and $12.57. Okay. For a truly continuous variable, the probability of ever having any of those values is 0. So it's like you add in a few variables. Yes, you could use bins, but that's a coarsening. That is moving. You start to do that though, Eduardo. And what you're doing is that's no longer the unconfoundedness assumption. The unconfoundedness assumption is not so mechanical like that. I mean, ultimately, Eduardo, that's probably what you're going to need to do. Coarsened exact matching by Gary Khaing. That's what he does. He coarsens the variables. And then once he coarsens them, then he does exact matching. But it's like a bit of a mechanical fix. You've not ultimately fixed the problem. You've just you've redefined the problem away by just saying, because then you're mismatching within each of the coarsening parts. Okay. So stratification requires having units in both groups for every value of X to get the average treatment effect. If you wanted the ATT, you didn't need it. Okay. And then we're going to take a break. So you see it. As you add in more variables, the dimension grows faster than the number of variables. For each new variable, depending on how many values there are and on how many other values there are for all the other variables, the dimensions grows way faster. And very quickly, you can have more dimensions than you have data. And that's called the curse of dimensionality. When you have more dimensions to the data, then it's even possible for you to satisfy theoretically, because you would have to have units in both treatment and control for in each of those K. At some point, there's not enough data. So here's the number. If you got number of strata, you've got 10 variables, each of which take on 3 categories, 59,000 dimensions to the data. It explodes. These are slices of all interactions of the covariate set, because what you're doing in this is you're saying 4 identical people. Nobody is just a man and just a child. They are a male child. They are a female adult, right? You're not a female. You're not an adult. You're both of them. You're both of them. So you've got that's where the unconfoundedness is really working. It's working at the level of identical groups of people, but you're going to need more than that. So when some slice is empty cell, which is, I think what, wasn't Jeff, it was, someone else, Jeff Carter. When some slice of the data, some dimension to the data, adult males, female children, if you have an empty cell, and that's what this was, empty cells. Nobody's in, there are no female children there. When you have empty cells, you have the curse of dimensionality, and you can't match or do any kind of manipulation within that dimension of the data. And that's why, that's another reason that this throw a bunch of variables in the data set also creates an issue. It's not just the collider part. It also creates a curse of dimensionality part. You may not have that quickly is going to just collapse. So what is nice about this is that the matching methods force you to realize, can I even do the matching? Regression does not use common support. Regression uses extrapolation. It imputes off of the relationships between the X's and the outcomes in one area and then imputes. But the only way it can get it correct, the only way that extrapolation is correct is if the model is specified correctly. Okay. So here's a picture of no overlap. So without any common support, you don't have a bridge. It's like an incomplete bridge. I actually haven't. Yeah, probably. I don't see why you couldn't do that. You'd have to, but I don't actually know what you would do, Renz. I mean, you'd have to have, what even would you do? I'm not positive, to be honest, because you'd have to bound both the outcome and the number of observations, because you'd be bounding the weights, not positive. Empty cells implies no overlap for that strata. Correct, Sergio. Seems like you could, Renz, in principle, do something like that, but you'd be bounding on two dimensions. You'd be bounding on the weights and you'd be bounding on the average outcome. So I'm not positive, you could really blow it up by having like huge weights. So I'm not really sure. I'm not positive. I haven't seen anybody do that. All right, let's take a break. 22 minutes on the hour. We'll come back 22 minutes on the hour, 15 minutes. Okay. And then we'll look at exact matching. All right, let's get back to where we were. Okay. And now we're going to look at this exact matching. So everything when it comes to matching that or weight or propensity scores or inverse probability weighting, anything like that, that's based on the covariates, that's not a regression, everything really is hinging on, can you justify unconfoundedness and common support? Now, most people don't know anything about common support because the only thing that they've really ever learned was regressions. And regressions don't use common support. Regressions use extrapolation to impute missing counterfactuals based on the functional form of the model, which we're going to talk about later. But if you are if you are satisfying unconfoundedness, it's all going to come down to this. So if you've got, you are satisfied with assuming unconfoundedness, right? Then there are two broad routes to take. Number one, the common support route. Okay, that would be matching, weighting, methodologies. Okay. And then there is the extrapolation routes. That's OLS. And even then with OLS, the functional forms matter. The functional forms are are what you need instead of common support, which implies particular specifications will work and others won't, even for the same covariates. Okay. So this is kind of this is the route we want to take, which is like, you can either go this route or you can go this route. So what we're going to do is we're going to start here, then we're going to go over here. Okay. We're going to start here. We're going to go over here. We're going to start with exact matching. Okay. So matching goes back to Rubin's early work. But we're going to start later. We're going to go to nearest neighbor matching. All right. As there's a bunch of ideas that we're going to draw upon later. Well, we're not going to do it in this workshop, but there's a lot of ideas in exact matching that show up again in synthetic control. And they actually show up a little bit with difference and differences. So there's reasons to do this. Okay. So matching, what it does is you match a treated unit to a comparison unit that's identical on those known and quantified confounders. That's what you're doing. And if you can't find one, like we couldn't find a female child in treatment group, correct. Vast majority of, well, not even just economists, the vast majority of everybody goes the second route, regressions. But as we're going to see, they're and this is not arrogance to say this, they are absolutely, by and large, misspecifying the regression model. Because what we now know is with heterogeneous treatment effects, it really matters how you specify the regression model. Whereas when we learn econometrics or regression classes, remember, you never learned anything in terms of potential outcomes. So you never had this like issue with heterogeneous treatment effects. So, but once you introduce that, not all the OLS models will get you the same parameter. If you want to get the average treatment effect versus the average treated on the treated, well, what's the specification for that? And most of us just go, well, isn't it just regress y dx? But that would only give you one coefficient. So how would you get either one of them? So that's what we're going to kind of build to. All right. So if you cannot find a unit in both groups that are observationally equivalent, mine too, it means common support failed. And if common support failed, then what we've got to do is remaining in that route here. If common support fails, then we have bias, but the bias is coming from common support failing, not coming from the unconfoundedness at home. So there's two ways you can get bias. That's the thing you want to see. There's two ways you get bias in matching. Number one, unconfoundedness isn't true. That means you didn't control for confounders or you controlled for colliders. All right, either one of those, the X conditioning set is wrong. Versus two, common support doesn't hold. And when common support doesn't hold, it's called matching bias, as opposed to selection bias. Although maybe that's not even the right way to do it, but it's a different kind of bias. It's a bias that comes from not matching exactly the right people. So that's why I was saying, to Eduardo, he said binning it, but if you bin it, you will be matching people that aren't necessarily the people that you're wanting to be matched. You'll match within the bin, but technically the identifying assumption is at it depends on what the unconfoundedness assumption is. If the unconfoundedness assumption is with respect to the bins, you're fine. But if the unconfoundedness assumption is with respect to the covariates, the binning is just, you would have to make additional assumptions to be sure that the bias isn't there. Like you'd limit the heterogeneity or something within the bins. That's right. Well, if you cannot satisfy unconfoundedness, then matching, it will still be biased. Okay. So that's what I was saying is that, if you're using regressions, matching, weighting, anything with covariates, double debiased machine learning, causal forests, it is assumed that you are satisfying that. Anytime your solution to the causal inference problem is to use controls, you're assuming that you have the right controls and none of the bad controls. But then you still have to kind of decide what the estimator is going to be. No, Jeff, you got to keep it separate. So you can have bias from unconfoundedness not holding. That could mean including a collider. That could mean not including an important confounder. That's totally separate. Unconfoundedness fails because you either have colliders in there or you don't have the covariates that you need to satisfy that conditional randomization. It's all that it means. Unconfoundedness means that you have randomization of the treatment within the dimensions of X. The bias that we're talking about is matching bias. Matching bias means you do not have common support. You don't have any 45-year-old white bald men in both treatment and control. So you match 40-year-old white bald men with 45-year-old white bald men. Well, if unconfoundedness is with respect to age, race, hair, sex, that's a mismatch. And technically it can introduce bias. If you have a bad covariate It's this over here. This is the bad control stuff or not having the right controls. This over here is matching incorrectly. Matching incorrectly. They have to be exchangeable. And the exchangeability is within the dimensions of X. Okay. So let's look it up. I see you typing, Jeff. Oh. No. Sorry. If I did say that, that wasn't correct. I was trying to say there's the selection on observables, and then there's the common support. And they're two separate problems. And you need both for these non-parametric methods like matching and weighting. But for regression, you don't need common support. But you do need the functional form to be correct. And that's its own problem. Okay. So here we have a training example. All right. We have group of units in a job training program. A group of workers that aren't. Okay. You can see here, I've got their age and I got their earnings. All right. Their average age, 28.2. Average age over here, 32.85. So they're very, very different. Two groups are very different. So I do not have the same mean age. And the older that you are, usually people make more money as they get older. So this is an important confounder. If you believe that this is, a predictor of higher wages, then the fact that the distribution is different in the two groups will automatically create bias. Okay. All right. So look, people in the treatment group making 24,000, people in the control group making 27. If we did a simple SDO, negative $3,773, it would say, and that's true, that's not causal, but it's true. People in the trainee program make $3,700 less than the people that aren't, but the people in the trainee program are much younger. Okay. So let's look at the age distribution. All right. You got a lot more mass here. Oh, they're spread out everywhere here. Okay. So exact matching. Exact matching finds someone for whatever parameter that we're trying to estimate. Okay. You have to match 1-to-1. So let's say that we're doing the ATT. If we're doing the ATT, then we have to find a 31-year-old over here. There's one right there. There's a 31-year-old. There's a 31-year-old. We can use it. We can choose to use them twice or not. Okay. We can choose to use them twice or not. 18-year-old, where are they? There's one. 32-year-old, where's that one? There's one. And there's one. 32-year-old, right there. Right there. 25-year-old. There. Yep, there's a 32-year-old again. We're using them multiple times as matches. We have to do, there it is again. 20-year-old. Right there. 29-year-old. Right there. And right there. And right there. Okay. So we have to kind of decide. There's some stuff. Is there a 32? Okay. Where? Yep. Oh man. Tons of 32s. Tons of 32s. So we have to decide. So you see how there's all these matches. So what we're going to do is we have the trainee group. We have the non-trainee groups. But look, we're only going to use, if we want the ATT, we are only going to use those units. We're not going to use the 46-year-olds. Why? Because for the ATT, they don't matter because this is only people in the treatment group. So we have to match for them. If we wanted the average treatment effect, we would have to find comparison groups for this group, but it's not possible. There's no 46-year-olds over here. Okay. So we're going to look at the ATT. Focus on the ATT for the rest of the day. It's a lot easier if we just stick with one thing. So we're going to do the ATT. There it is. That's the estimate. There's a 32-year-old in the treatment group. there's a 32-year-old in the control group matched with that one. We're going to look at that's their earnings and that's their matched earnings. That's their estimated counterfactual earnings had they not been in the training program, which under unconfoundedness, we are allowed to make that substitution. We're allowed to make that substitution. And the reason is because if we just go back, Y0, okay, with that assumption, it is allowed to write this down. Expectation Y0 D equal 1, X equal X equals expectation Y0 D equal 0, X equal X. We're missing this. That means we're missing that. So what we do instead is we use this. We use this instead because they're on average the same. Individually, they're not correct. On average, they're the same. You see what I mean? So we're not saying that every one of those 13-year-olds literally have the exact same wage as what that person would have had. We're saying, well, under unconfoundedness, the average is correct. Yeah. Here. Okay. ATT. Effect, average causal effect of a training program on earnings for people in the training program. So it's only for these 10 people, okay, versus 30 people. So 10 people only. ATE, average causal effect of a training program on all 30 people, regardless of whether they had been in the program. Because remember, each person has an individual treatment effect. So we're just going to be summarizing it. And then the ATU would be the average causal effect of a training program on the 20 people in the control group, despite the fact that they didn't participate in the program. Okay. All of them different. So we're going to just focus on this one. The ATT only requires two assumptions. Y0, that's the first, weak unconfoundedness, and, you know, at least one unit in both in the control group per strata. Okay, at least one unit in both treatment and control per strata dimension. Here we only have one. Here the only strata is, here the only covariate is age. And we have, you know, 1, 2, 3, 4, 5, 6. We have 6 strata because we got, you know, 32 is showing up 4 times. 31 shows up twice. So we only have 6 strata. We have to match within those 6. Okay. All right. And there it is. Whoops. There it is. So there's the matching that you're going to do. And if you find 2 or more units with the exact same age, then you just would average them. You'd average over the number of matches. Okay. But notice that all we're doing is dealing with Y0. Because if you go back, remember, write down ATT. ATT is expectation Y1 D equal 1 minus expectation Y0 D equal 0. We can replace Y for Y1. We cannot replace anything for Y0 because it's missing. We can write down ATT is equal to expectation Y D equal 1 minus expectation Y0 D equal 1. That's missing So we match on that one. That one we don't do anything with. It's fine. That's why what that means is that, we're going to work with this average here. We're always going to work with 24,150. We're just not going to be working with that average. Okay. We're not going to be working with that average. All right. So here's the algorithm. For each unit in the treatment group, all 10 people with their age, find every unit in the control group who has the same age. If you find more than one, take the average. All right. It can be one or it can be greater than one if you want it to be, whatever you want. For each unit I, for each person in the treatment group, replace their missing potential outcome with the matched outcome from step one and do it for everybody in the group. So that means 31, we have to make like a match sample over here. 31-year-olds, make a match sample 25052. We're going to have 10 people, 10 numbers. We're going to take the average. We're going to take the average and difference it. For each unit, calculate the difference between realized earnings and matched earnings, and then estimate the sample ATT by averaging over all differences in earnings from step 3. And you're done. So here's the match sample. 31-year-old, 31-year-old. We're using them multiple times, but notice age has the same average. Mechanically, it has the same average. You've forced it to have the same distribution. You forced it to have the same distribution. There's same number of 31-year-olds, same number of 18-year-olds, same number of 32-year-olds, and so on. They have the same distribution of age in both groups. The groups with under exact matching are perfectly balanced. Perfectly balanced. Okay, the mean's the same, the variance is the same, skewness is the same, kurtosis is the same, all that stuff, all of those, all those measurements are identical in both groups. So that's created perfect balance. And then under unconfoundedness, you're allowed to just take it. So now we take the average, 210. Messed up something. Oh, I did something. Okay, I'll have to go back and check that. But basically, it looks like must have carried over the math wrong. I'll fix it. So then we get 24,210. We go over here, and we now get a positive treatment effect. Yeah, you take the average. That's usually what's recommended. You could just take one person who was 32-year-old Ian, but you'd have to kind of like randomly pick of all the 32-year-olds. You'd have to do something like this. So it's like if you're wanting to do 32-year-olds, you'd have to say randomly pick one of the 32-year-olds with replacement, randomly do it. And so usually what people do is they just take the average. Although it does kind of matter a little bit for inference, but yeah, Sheree, I gotta like fix this. There's all kinds of stuff. I've got to like spend a little bit more time on this exercise because there's all kinds of reasons I'm not crazy about it, but I'm gonna fix it. So for now, though, this is kind of like a manufactured sample, and it's just for teaching purposes. But I gotta fix it up. I gotta clean it a little bit. Okay. You can't. If you do not have a match for a specific category, you cannot use exact matching. And if you drop a unit, Eduardo, if you drop a unit, it's no longer the ATT. It's no longer the ATT. As you start trimming the data, you're moving away from the parameter. Okay? So it's because the parameter is all about these 10 people. You drop any one of them, it's a different parameter. Okay, good. But here's what you can do, Eduardo. You could actually move in a different direction and use inexact matching. Okay, you can use inexact matching. So let's look at what inexact matching is. No, the partial identification would be when you make you sort of remove some assumptions and you sort of put in there, like there's different ways that you can make different kinds of even weaker assumptions than what we're doing. So that's different than this. This is still using independence. Probably. Cash, I bet you're right. I need to, that's what I was saying. As I was looking at it, something didn't look right. So I need to go in and see what's going on. Let me just make a note. I'll look at it and figure out what's going on. So fix the exact matching exercise. Wonder if I actually have this worked out. Let me remind myself why it's all colorful here. So here I had raw data. Okay, here I had raw data. Okay, so you have raw data. And when you calculate the SDO, right, so here you go, you take the average of that, and the average is 11,075. Take the average of this, 11,101. Yep, exactly, Sebastian. Like here's an example of the exact match. Well, this is exact matching. So here we have exact matching. Okay, so we have exact matching, and this one's going to be okay. So I'm not going to do the I'm not going to do the not going to do what am I saying? I'm not going to do the two variables. I'm going to show you this right here. So here you have people on this treatment. Okay. And we're going to find exact matches. So here's an 18-year-old. It's going to match with that guy, which is unit 14. Going to put him right there. Okay. Could actually do it a little better. Right. We go here to the 29-year-old. Where is he? 29-year-old. There. Okay. What about the 24-year-old here? What about the 27-year-old there? What about the 33-year-old? Got two of them. So what am I going to do? Well, it doesn't really matter because they're exactly the same. I still don't like this exercise. So then we're going to do the 22-year-old. It's here. Then we're going to do the 17-year-old. No, we're going to do the 19-year-old. 19-year-old there. You go to 20. You go 21. You go 30. Okay. So we exactly matched. And now we take the average, 11,075, 94667. Okay. So that's going to be equal this minus that. That's the estimated treatment effect. Okay. Right now we're not doing propensity score matching, but you know, when we work, yeah, right. Yeah, exactly, Eduardo. So it's one of the advantages of the propensity score is that it has the ability to make this a lot easier to do. So there you go. That's it. Okay. But what if there was like a, you know, 50-year-old? There's no 50-year-old in here. Can't do it. Not with exact matching. So there's inexact matching. All right. So if there are no matches that can be found, it means that there are cells that contain, well, we already know what it means. All right. Okay. So what we're going to do is we're going to use nearest neighbor matching, and then we're going to use bias adjustment in a paper by Alberto Abadi and Hito Embens. Okay. So we're going to have inexact matching, which violates common support. And the bigger the matching discrepancy, the bigger the bias can be. But we're going to use something called bias adjustment to try to correct that for that bias. Okay. All right. So here we go. Nearest neighbor matching. And that might be where we conclude. We may have to do propensity score matching on Saturday and regression on Saturday as we lead into IV. We might be able to get to propensity scores. So nearest neighbor matching, we're going to estimate the average treatment on the treated by imputing the missing potential outcome by using the person who's the closest, has the closest value of the covariate. It's this closest part that's going to really drive everything with nearest neighbor matching. Now with age, it's pretty easy. When you have, okay, we'll get to that in a second. So we could use this the same thing as before. So here we have one covariate. Okay, we have one covariate. And we have here the treatment group, and we have the treatment group here. Okay, we want the ATT. This is the treatment group. This is their outcome in a world where treated. This is their outcome in a world where not treated. We're missing that one. Okay, we're missing Y0 for the treatment group. So what we're going to do is we're going to use X's and grab a neighbor. All right, we're going to grab a neighbor. So here, okay, let's grab a neighbor. There's a neighbor. It's got the same X. So we're going to move this to there. Okay, so we move that to there. Person 2, missing that counterfactual, of course. Here we have a 1. What's the closest person whose covariate is closest to a 1? It'd be this guy. Okay, so we're going to take this 0 and put it there. And then now we go to the last person, 10. So we have to figure out who is the closest person to it. Now, here's where you had some choices you have to make. Are you going to let people be used as a match multiple times? Or are you going to say, well, once he's used as a match, I'm going to throw him out? See, the more that you throw out these good matches, the more that you do it, the more bias you're going to have. Yeah. So it's recommended that you put these people back in and move and use them more than once, but you have to do a standard error correction that accounts for using them multiple times. All right. It's called the Abadi-Embens standard error. So we're going to go here, 10. That's going to be this person. We're going to use them again there. Okay. So now we're going to get a estimated treatment effect, 6 minus 9, -3, 1 minus 0, +1, 0 minus 9, -9. 1 minus 3 minus 9, -11, divided by 3. That's -3.67. Notice how the weights are identical. So with exact matching, it's different than that sub-classification method. With exact matching, you're not calculating weights. that like do this re-weighting. Instead, you're doing imputing and then you're doing equal weights. It's kind of interesting. Weights are always in there, but like when it's a direct imputation, everybody gets weighted the same. But when it's like, taking the averages and then kind of re-weighting them according to the distribution of those covariates, then the weights are different. Okay. So that's pretty straightforward. But what if we're over here? What if we're over here? Okay. We have two covariates, right? So it's like unit one. Who's going to be his closest person? He's 18 years old. Are we going to match him with the 19-year-old? 1.28 GPA. I think it's that guy. Are we going to match him with him? Or are we going to match him with them? Okay. So we need a formula. It's not as simple now, is the point. So when you have multiple covariates, it's this idea of closeness that gets new. Okay. When it was one variable, it was really simple because it was a number line and you just looked for whoever was closest. But when it's like when it's multiple variables, then, and they all have different units of measurement. It's like even the dimension idea is not going to work. Okay. So, because you're not using exact matching anymore, you're using distance. You're using distance. And so you're trying to minimize the distance. Okay. Trying to minimize the distance of the matches. It's a little bit of a different idea than we've seen before. So we have to figure out, what is distance? What does it mean to be far away on two dimensions, GPA and age? What does that mean? Right? Okay. So what we're going to do is we're going to take a 15-minute break. We're taking a 15-minute break and we'll come right back. Okay. Abity. Sebastian said, what was the standard error adjustment that you have to do? And we're gonna discuss it, Sebastian, but it's called Abity and Imbens robust standard errors. The AI standard errors, they're you have to, it's if you use the same person more than once, you have to adjust for it. And so we're gonna look at it. Okay, so what does it mean to be close when I'm working with a large number of covariates? We have to find a distance measure, and there's lots of ways to do it. So we're going to work with the first one called the Euclidean distance. Before I put the equation up, I'm just going to show you the Euclidean distance, okay? Because I think it's easier to understand if you can just sort of walk through the spreadsheet, okay? So we're back here with this spreadsheet. Oops, sorry about that. Okay, so we've got there, that right there. And I'm going to show you 3 examples. Yeah, it's different. It's different, Eduardo. It's not a regret, yeah, it's very different. So, okay, so, okay, I'm going to show you 3 examples. And here's the first one, and ask me any questions as I go. All right. So here's my training group. Here's the people that are in the job training program. Here's my comparison group. Correct. For any number of covariates more than 1. Yes, exactly. All right. As many as you want to. I don't know. No, there's no reason it couldn't be very large I don't see a reason it couldn't be. So here you go. So you've got training group, 2 different variables, how old they are and what their high school grades were. Their high school grades go from 0 to 4. It's called a grade point average for those that don't, and from the United States. So you have units, all this stuff. There's their earnings, comparison group. They're very different they're hugely different. So the SDO is very different. Okay. And I'm going to do this. I'm going to take a random match and so I can show you something. Okay. I'm going to illustrate something. So I got a random match. All right. I'm going to take that guy, that guy, etc. All right. So look what I have now. Got the average age, actually made it worse. And the GPA is the same. All right. Okay. So here you have here's what you have. You have the average and the average. Okay. So you take a match, you take the averages, you difference them. That's your estimate of the ATT. Okay. But what we're trying to figure out is which units should we put in this column here? Which units? And we know it's going to be some units that's like closest. We got to figure out what that is. So look at what this is. All right. I've got this thing I'm calling squared gaps. Here's what the squared gaps is. All right. Once I make my match, I take the age minus the age and I square it. The reason you square it is because you want to get rid of the negatives. You want everything to be positive for what we're about to do. Okay. So you do that for all of them. You also do it for GPA. And then you have, all these squared gaps. Now, what are these measuring? If you think about it, what are these squared gaps? What do you think these squared gaps are why are we doing this? What do you think the purpose of this is? If you had to guess. Yeah, distance, error reduction. Big gap, no good. Yeah, exactly. This is kind of our way, right? This is our way of showing how bad the match is. This is our measurement of the discrepancy, the matching discrepancy. So what I'm going to do now is I've gotten these gaps. I'm going to add them together. Okay. There it is. 2093.61. 2093.61. And then I'm going to take the square root. All right. Now look, ask yourself, I wonder what the units are for this. 45.75 what? What is it? What are the units? What do you think those units are? 45.7. Yeah, exactly. It's kind of like not real. It's kind of nonsensical because all it is like it basically pretended as though these were the same units. If you think about it, it kind of pretended they were the same units. Otherwise, how did we add them together? How could you add 10 chickens and 45 degrees Celsius, right? Can't add those together. So but they're both numbers. So what this is called is the Euclidean distance. You could, yes. Right now we're not though, Jeff. Right now we're just doing what's called the Euclidean distance. The Euclidean distance takes the units and throws them away, pretends that everything is on the same units, which is obviously going to create issues. If you did any kind of transformation of the GPA, if you took like the log or you did all kinds of stuff, it's going to change it, right? So we're going to get to that in a minute. All right. So that's a 45. It's like the measure of the discrepancy. Okay. Now I'm going to take a second random match. Second random match. Bunch of other ones. All right. Look, that was a 34. Now it's a 31. That had been a 1.75. Now it's 1.736. They're both slight improvements. They're both slight improvements on those means of age and GPA. But let's look at the Euclidean distance. Okay, that Euclidean distance, that distance is smaller than that one. That had been 441. That was 16. I think not all of them are smaller. Maybe they all are. No. That one I think might be bigger. Let's see. Yeah. So like one of them got worse. But on average, 148 2,083. So on average, it cut the distance in half. All right. So let's add them together. 158.12 right there versus 2093. So it's half the distance. Take the square root, 32.5. All right. That's the measure of the gap, the matching discrepancy. But here's the estimate of the ATT. The estimate of the ATT does not use this information. This is just telling you about the quality of this sample. That's all it's telling you is the quality of the sample. So we go 1175 minus 1080.22, estimated ATT 252. All right. So here is the Euclidean distance. We do all the matches. Okay. We then take the gap. We square each of them. We sum them all. We sum all the squareds. Then we take the square root. Okay. So Abity and Embens all throughout like the 2000s and the 2010s, they just kept writing over and like Embens is the guy that just won the Nobel Prize. Abity's the guy that invented synthetic control, but they did a bunch of matching stuff together, all in the 2000s and early to mid 2000s, the teens. They've been a great team. So they show in this 06 paper that there is a unique solution to the matching problem. Okay. And that means that there is a single 10 observations that I could pick and put here that will have the smallest, Euclidean distance. Okay. And these programs matching in R and T-effects in Stata will follow that algorithm. Okay. It'll follow that algorithm that searches and finds the sample with the smallest distance into Euclidean space. Okay. So I drew a picture. So this, like right here, would be all possible matches. All right. This would be like all possible matches. And this over here is the Euclidean distance. There exists a unique match that minimizes the Euclidean distance such that even changing one person in the data will strictly increase the Euclidean distance. Okay, so I have it right here. Optimal match. Okay, optimal match. I had to use the algorithm and Stata to find it, but I got this optimal match. Now look, it's treating age and GPA as identical. It's treating age and GPA as identical. So what it ended up doing was basically matching here first and then matching on the continuous variable, because it was able to find exact matches here, but because GPA was continuous, it was never able to find exact matches. But the sum, 8.96 versus 1,000 versus 2,000. You take the square root of 8,000, 8.9678. It's basically a 3. And there is not a single match that will get you lower than 2.99. So like, let's look. So let's see one. So here I got a guy that's 30 years old. Let's use this guy. Let's use this guy instead. He's 33. So a 29-year-old, 28, 29. All right, so let's use that guy. Slightly different. Keep an eye on 2.966. A little bit bigger. See that? Changing even one person drives up the error. Just a little bit. Slightly lower. The true average treatment on the treated was 1608. When I did this, look, 1608. When I change it a little bit, the bias gets a little bit worse. Okay? What do you think? Pretty simple? Pretty simple? Suppose that GPA and age differ in the magnitude of their explanatory power in determining wage earnings. Would we want to use a distant metric that weights matching covariates by their relative contribution in the determination of earnings? It's all coming out of the unconfoundedness. If you have unconfoundedness, it means that the average Y0 is the same treatment control for each value of X. So it's not that you're using like, the explanatory power, you're using the unconfoundedness. That's the only thing you're leaning on. You're leaning on not really like, is this variable highly predictive of the outcome? Rather, you're saying these are the variables that I have to match on in order to satisfy unconfoundedness. And that's where we have kind of the known proofs. That's where we have the known proofs. So I have to think a little bit more, Jeff, about what you're saying. I'll think more about it. It's supposed to differ the magnitude. See, you're not trying to explain, though, earnings. Trying to explain potential outcomes. I need to think about it. Jeff, let me think about it some more. Because I'm just thinking out loud. We got some more questions. All right, I'm gonna come back probably when you get that question. I'm gonna throw it up here. Okay, but Jeff had brought something up. Maybe there's other distance measures, right? Because this is treating everything the same. But it's like having a 1.89 GPA and having a 2.6, having a 3.92 GPA versus a 1.8. True, it's only off by, 2 points. But in the United States, that's like basically, a person that barely passed high school. And this is a person that almost was like top of their class. So, yes, true, they're both 24 years old, but they're very different. They're very different from one another on that one. So our example kind of treated a 1 unit difference in age and a 1 unit difference in age and a 1 unit difference in GPA as though it was the same units. Okay. But the scales are different and they matter a lot. And you could like imagine. Yeah, it does. It's prioritizing age because it's prioritizing the number line. It's like, it's basically saying because here's what it's doing, Poppy. It's summing the squareds. So, that number is worse than that one, right? So you kind of are like already in this world where you're getting penalized because of the squaring. It doesn't really, you're not getting penalized because of the units, you're getting penalized because of the number. So if you can get that aggregate number down, it doesn't matter where you're getting it from for this Euclidean distance. So the Euclidean distance also is not invariant to the changes in the scale. So like if you took the log of income versus the level of income, that'll change a lot because differences in the log of income are going to be smaller numbers than differences in the levels, right? So you've got this kind of like stuff where even some like things that shouldn't really matter, am I measuring my income in dollars or am I measuring it in log dollars? Like, what's the difference? And, because it's like, it doesn't really matter. So what you would like is an alternative distant metric that does not depend on the scale. And Jeff kind of threw out some ideas. Is there a way to standardize the matching variable in some way? And there is. There's a normalized Euclidean distance, and there's something called the Mahalanobis distance. And they're both ways of sort of addressing using a slight adjustment such that like whatever scale it's in, it basically, it adjusts for it in a particular normalization. So the normalized Euclidean distance, basically what it's going to do is it's going to take the diagonal here of this like variance term and just use that variance to kind of adjust it. It looks like this. So this is going to be any changes in the scale of X. We haven't done it yet. You cannot do the bootstrap. Yeah, we haven't done it yet. So, but you cannot do the bootstrap because the bootstrap is something that Abity and Embens learned you can't do. So, I think it's a 2008, maybe. I'm not sure. Maybe the 06. But if you change the scales, but you also adjust the variance of it, then you've kind of, taken out the scaling. So it kind of all gets deleted. And you've got this normalized Euclidean distance. And then you got this Mahalanobis distance. It sort of does the same thing, but instead of the diagonal, it's the sample variance covariance matrix of the covariance. Okay. But the larger the dimensions of the conditioning set, what happens if we match on GPA? Should we do both? You have to do both, Ronald. You have to do both if you need both for unconfoundedness. So if you're saying up front, the omitted variables are GPA and age, you don't have an option. You have to match on both of them because that is what guarantees those are the covariates that guarantee unbiasedness. Okay. So larger the dimensions, less likely common support holds. But you got to have those covariate dimensions to satisfy the unconfoundedness. So you can't just drop variables. You're just going to have to deal with it. So the problem is coming from a finite data set, and it's introducing a particular kind of selection bias. But Abity and Embens, in this 2011 article, they derived a way to reduce the bias. And here's, I want to show you something real quick. All right. So if you think back to the STO, right? The STO was ATE plus what? Expectation okay. But if you had Y0 D condition D, then it would go like this. It'd go STO equals ATT plus expectation Y0 D equal 1 minus expectation Y0 D equal 0. Okay. So, and we're sort of focused on this ATT term. So look, if you have over here, all right, you don't have it with respect to both, but you have it with respect to one, the Y0 one, then your STO will equal the average treatment on the treated plus selection bias. Okay? Selection bias. When you have, so which will equal 0. It'll equal, if you have that, then that goes away. Okay. So if you have that right there, right? So under this scenario right here, you have with this, you can write down expectation Y0 equal 1 equal expectation Y0 equals 0. Okay. You can write that down. So that means even though this is the expression of the STO under this, you can go expectation Y0 equal 1 minus expectation Y0 equals 0. And you know that if this is true right here, then that's true. And then that'll go away. Okay. All right. That'll go away. So in this world where when you have unconfoundedness, okay, but not common support, what we will see is that the bias is not coming from expectation y0 d equal 1, x equaling x, not equaling it's not. Because that's true. Unconfoundedness gives you that. It's coming instead from the fact that it's coming from this expectation y0 d equal 1, d equal 1, x equal, xi is not equaling expectation y0 d equals 0, x equaling x ji. It's coming from the mismatch. The mismatch is creating selection bias. All right. The mismatch is creating selection bias. So what Abity and Embeds are going to do is they're going to derive the bias, then they're going to estimate the bias, then they're going to delete it. Okay. So let me show you. So we're going to write down the estimator. That's what this is right here. It's this. Oops. Okay. Average Y for the training group, average Y for the matched sample. Average Y for the training group, average Y for the matched sample. That's the notation for the matched sample. There's the training group person matched with that control group person. So this is like person 1 matched with person 14. Okay. 2 people with the same age GPA, but different Y. Now, if that's fine. That doesn't matter. It's only with respect to the X's, not the Y's. If you're minimizing the discrepancy, and then you're just whatever the Y is fine, because it's under unconfoundedness, it's correct. The Y's in the control group and the Y0s in the treatment group should on average be the same within the dimensions of X. So you can kind of trust the control group outcome, in the same way that in the RCT, you could trust the control group outcome. You knew it was true. Okay. Okay. This notation comes from Jim Heckman's work in the late 90s with Petra Todd, Jeff Smith, Hide Ikamura. They would do these mu terms. Mu here just means average outcome for individual values of X for the control group. And if it's the control group, then Y equals Y0. All right. And for that value of X. And if it's in the treatment group, okay, treatment group, the average value of Y is just Y1. Right. So that means like over here, earnings, it's Y1. Over here, it's Y0. All right. So that's all that it is. We just replaced earnings with Y0 if you're in the control group, and we replaced earnings if you're in the treatment group with Y1. Okay. All right. And then what I'm going to do is I'm going to say, all right, your outcome is going to be determined by that mean value. Okay. The mean value, plus some, little error term. It's going to be equal to that plus some error term. So they introduce a regression model. This is basically a regression model. All right. All right. So here we go. We're going to do that trick again where we add in a 0. We're going to do that trick again when we add in a 0, but not yet. So here we go. Y, yi, whoops. Yi, so that's going to be treatment group Y. Treatment group Y should be Y1. Should be this one. So treatment group Y is actually Y1 is actually mu1. right? So there it is right there. Okay, plus the error term. And then this is mu zero, but it's for the match sample. It's for the match sample. So we have, you know, that's y zero, and that's mu zero. Okay. And we're going to have mu zero plus error because we said down here that the outcomes are equal to the mu terms plus the error. All right. So this is how they're introducing some noise that they're going to use. All right. So we got here this expression, and all we're going to do is just kind of move this piece over here, and then we're going to move this piece over here. So you can see now we just kind of moved some stuff around, and then we just distributed that summation operator, right? This averaging operator, okay? All right, so we got that. So the sample ATT, there's nothing causal in here, all right? There's nothing causal in here. This is the average Y for the treatment group, and that's the average Y for the control group in the match sample, all right? But they've been mismatched slightly. All right. This right here is the bias of the ATT. So if you look right here, here's the estimate minus the truth. There's the estimate. There's the truth. 1607.5 minus 1608. It's off by negative 0.5. No, you shouldn't. Eduardo, you just let it do it. You're going to use this formula I'm about to show you. You shouldn't start guessing. You should use things that have known properties. So we're going to show you what you're going to do, okay? All right. So here, right? So you do this. I did that here. Its bias is negative 0.5. You don't know this bias. All right. I only know this bias because I knew what the truth was. But so you don't know what that is. But we're writing down a theorem, kind of. We're writing down, say, like, you know, here's the estimate, there's the truth. Any difference between them is the bias. All right. So he writes it out. There's the ATT. There's the estimate of the ATT. There's these two error terms. Right. Now here is the innovation, or not the innovation. They're going to do something. They're going to add a zero to the right-hand side. And here's the zero. Mu zero xi minus mu zero xi. And we'll say it's like 1 over n sum d equal 1, right? So you're like summing over the treatment group, and we're basically just going adding in a zero. So that's equal to 0 because that number and that number are the same. So you've added a 0. You've not done anything. But let me show you where it is. There it is right there. Okay. So I added it in and then I moved it around. I put this term up here and then I put this term down there. Okay. Now look super close. That is the ATT for each. It's the true. Look, that's person 1 had they not been treated. Counterfactual. We don't know what it is, but that is their potential outcomes had they not been treated for the treatment group. So you take all of this, subtract it row by row. It would be basically like, you know, that's the estimated treatment effect, but it would be basically like the truth, row by row. There's the average. Okay, that's for the estimate, but it's the same kind of idea, only you'd have the true treatment effects. You take the average, that's going to be 0 because that's going to be the ATT minus the ATT. That's going to be gone, right? Which is understandable because here's the, you know, so part of it's getting deleted out. These are on average equal to 0 in a large sample. Even for the match part in a large sample, this will be equal to 0. So they're going to go away. So in this That's going to go away. And all you're going to be left with is the bias of your estimator. And your bias is Y0. Here's your bias. Matching bias. It's basically expectation Y0, D equal 1, X equal X, I, okay? Not equal to expectation Y0, D equals 0, X equal X, J, I. That's your bias. It's a version of selection bias. It's basically said, I got matched with Ronald, okay? And Ronald's potential outcomes in a world we're not treated, I can see it. I don't know what mine are, but I know that me and Ronald do not have the exact same X's. And so we've been mismatched. And so insofar as for people with the same characteristics as me, you can calculate my Y0, and you take the people with the characteristics of Ronald, you calculate their Y0. If it's not the same, then it's bias. And if it is the same, it's not bias. But that's the form of the bias. The bias of matching is coming from the fact that you have units that are different from one another in the covariates. You've matched them. They're different, and along their particular strata, because the strata is not the same, because of that particular strata, if their average Y0 is different, you've got selection bias. It's just like we found earlier. It's just now it's solely in terms of the X's. Okay. So they come up with a trick. First, though, here's what they find, right? So if you allow K to get very large, so you can allow, they do this like central limit theorem. They say, well, assume N goes to infinity. Assume N goes to infinity. Well, if N goes to infinity, you'll have good matches. Okay. In the limit, you'll have like, perfect matches, but the bigger the dimensions are, it'll converge to 0 very slowly. See, we're always working with these finite samples. So it'll converge very slow as the dimensions get larger, because you're needing like large number of observations within each of the dimensions. So it's going to have to be like, a huge finite sample in order to kind of approximate what's happening. Okay. So that convergence is very slow. All right. The difference between the potential outcomes is also going to be very slow. And this right here may not converge to 0 at all. It can be very large. So this is like the discrepancy between the two. And then this also may not converge either. Okay. Because the matching discrepancy can dominate the matching estimator. So here's what they do. Bias is often an issue when we match in many dimensions. The bigger the dimensions are, the bigger the bias can be. Depends on the heterogeneity. So here is their solution. Because Eduardo is like, well, maybe I should do this and maybe I should do that. And everybody's kind of trying to come up with their own fix. All right. But unless you have proofs behind these things and theorems, it's kind of a stab in the dark. Not all the things that we've come up with actually work. So let's see what they came up with. So the bias is caused by large matching discrepancies. Here's what you can do. First of all, you can check in the data to see how well we're matching the covariates. All right, so that's how well we're matching. You can always improve your estimate of the ATT by using a very large control group. But most of the time, you're using all the data that you have already. So some of this is like Abity and Embin's kind of saying, yeah, statistically, the more controls you have, the better. But, most people just use all the data that they already have. And if the matching discrepancies are large, we need to use bias correction methods. So what is bias correction? All right. So think back to what they just found. Okay. Think back to what they found. Here's the matching discrepancy. This is different right here. This is different by this. And this is what each unit's contribution to the bias is. Every one of the treatment group units is contributing this to the bias. They're both contributing this like difference to the bias. All right. There it is. Each treated observation is contributing that to the bias. Okay. Bias corrected matching is going to estimate this and get an estimate of that. Using a regression model, then it's just going to delete it. Since this is the bias, you're just going to get estimates of each treatment group's bias, and then you're going to delete it out. Let me show you what he does. Okay. So number one, right? Number one, let's think really carefully. Mu zero is what? It is expectation y, okay? You know, expectation y condition on x equals expectation y zero condition on x without specifying the treatment group. Well, I guess this is for the, if it's xi, it'll be for d equal 1, xi d equal 1. And so, you know, that's what that one is. And then, all right, so I'll just do xi. And then this is like xji. This is the match sample. Okay. All right. So here we have these terms. Okay. And what we're going to do is we are going to get estimates of each of them, because if we have estimates of them, we might be able to delete them. All right. All right. Sorry. Okay. Here we go. Oh, that's what I was going to say. So what I was going to say is, what is it that's missing? What is it that's the source of the bias? The source of the bias is Y0. Y0 is driving the bias. So we've got to find data on the Y0s. And the only data on Y0s is for the control group. For the control group, the outcome is a Y0. Okay? Not for the treatment group. For the treatment group, the outcome is a Y1. So we can't do anything with the treatment group. But if we're trying to get an estimate of Y0, then we've got to find the units with Y0s. And the only one is the control group. So this is what we know. What do we know? We know, interestingly, under unconfoundedness, expectation Y0, D equals 0, X equal X is equal to expectation Y0, D equal 1, X equal X. So whatever this is, it's equal to this. So we can just work with the control group, and whatever we find, it'll be relevant for that also. Okay? This is like I have this I'll let you listen to it in just a second. I'll let you listen to this interview with Hide Ikamura. So we're going to regress Y on X with OLS, except only use the control sample. And we're going to relate Y0 to the X's. Okay? We're going to regress Y onto the X's because the X's determine the Y's. All right? The X's determine the Y's. So we're going to see what the relationship is. We're going to get these estimates of these coefficients. Once we get a regress, so it would be like this. It would be like, okay, it would be like reg survived onto adult, it'd be like onto age, sex, if first class class equals 0, okay, then you would say predict survived estimate. All right. And then you would have estimates of survival for every person. So you'd have list, survive, first in 1 to 10. Whoops. Okay. So you've got here, they are survived, but in first class, their probability of surviving was 19%, 0.19. Okay. So you used the constant and you used the coefficients on each of the variables to then predict the outcome. Because under unconfoundedness, whatever the relationship is between X and Y0 for one group, it's the same for the other group. It's the same for the other group. Under unconfoundedness, whatever is true for one is true for the other. So all I got to do is say for this group, look at the relationship between Y0 and X, whatever it is, it's the exact same over here. It's the exact same over here. So it's a trick. It's a subtle thing that's kind of contained in that unconfoundedness assumption that no one had ever taken advantage of it before. You then subtract. You'd get some estimate of Y0. You have to basically go regress Y0 for this group, for the match sample. For this group, regress Y0 onto both of those, get coefficient estimates, predict not only this, but also predict this. Then once you have it, since that's a source of the bias, and that's a source of the bias, because remember, that's the sources of the bias. You're going to delete it right there. You're going to delete it. Here's your estimate treatment effect. That would be right here. This is your estimated selection bias from matching discrepancy. So you would be basically just like 1450 minus whatever that was. And then the last thing would be to calculate a robust standard error called the Abadi-Embens robust standard error to get a standard error and then use those to get confidence intervals. Okay, so this would be an example. So here we have the estimate of the ATT. Okay, I did the matching. 10 minus 8, 4 minus 1, 10 minus 9. 2, 3, 1. Okay, and that's my estimated ATT. For the bias correction, what I do is I go right here, okay, and I regress Y0 onto X. I get a coefficient on X, and then I use that to impute each of these terms missing counterfactuals. I pull them out. See, they're slightly different X's because remember, I have used 3 for that one, but I used 4 for that one. I used 1 for this one, but I used 0 for that one. And I used 10 for this one, and I used 8 for that one. And I'm just basically predicting, that's my like formula. Everybody's Y0 is determined by that predicted formula. Because whatever it was for the control group, it is assumed to be the same for the treatment group. So I'm going to use every person's sex and age multiplied by this, plus this multiplied by this, plus constant times that, and get a predicted Y0. It's a predicted Y0. It's not predicted. It's predicted survival for the people in first class had they not been in first class. And then it's predicted survival for those not in first class had they not been in first class. You have to do both adjustments. and it slightly changes it, 1.33. Okay. So I'm gonna almost be done. So matching bias arises because of these large matching discrepancies. And that's happening because you do not have common support. So to minimize it, use a small number of M, use matching with replacement, use covariates that have a large effect on Y0. Jeff had kind of said, do I want to match on things that have high explanatory power of determining earnings? You want to match on covariates that have a large explanatory value on Y0, not earnings 0. Where's the earnings 0? In the control group. You would look at a bunch of covariates in the control group. If you don't know the DAG, you look at a bunch of control group, you look at your control group, regress earnings onto all the covariates, whichever ones are highly predictive, that's the one you want to try to match on if you don't know the DAG. And I get it, like we don't really know the DAG. So I'm trying to kind of like give you a full holistic view about how to go about this covariate selection. Here's the large sample distribution for the matching estimator so that you can get a standard error. Cannot use the bootstrap. So Abbott and Embens derived the variance. So matching estimators have a normal distribution in large samples. For matching without replacement, the usual variance estimator is this. Okay. But for matching with replacement, you'll use the same one over and over. You've got this first part here. Look, so that is the same. The match is different. The matches are different because you're redoing it. So you've got matches being a little bit better. All right. But you've got this new part where you have to account for the fact, the standard error has to account for the fact, the variance has to account for the fact that you're using units over and over and over. Okay. So K is the number of times an observation I is used as a match. So we had person 32 used 4 times. 4 times 3 is a 12, multiplied by this variance term divided by the number of matches squared. Okay, so we only had 1 match. Maybe we had 2. Let's say it was only 1 match, but it was allowing us to use it over and over. So that would be like blowing up. If I'm using that guy, all of a sudden the variance associated with him, the numerator is getting bigger by 12, multiplied by this term right here. And that'll give you an unbiased estimate of the variance, but it will be larger. But it needs to be larger. The variant, if you don't do this, the standard errors are too small. Okay? Standard errors are too small. So, can't tell what time it is, but I'm pretty sure it's time to end. 5:06. All right, so I got to think about what I want us to do this week for like homework. But I want you to go ahead. It's a lot to take in. We have the Discord channel open. I'll send out an email with the new recordings. Okay, I'll send out the email with the new recordings. It'll probably be like 3 hours from now. Post that. I'm going to think about what I want you guys to have as homework. And then after I get that, I want you to know we're going to finish up OLS on propensity score OLS kind of first half of Saturday. Then we're going to go into IV second half. It'll probably spill over a little bit to Sunday, and then we'll do RD on Sunday. Okay. So I have some Stata simulations I really want us to see, but I need us to get to the end before we see it. I think you're going to be amazed, to be honest, when you see what I'm going to show you. I think you're going to be kind of amazed. Okay. So sorry I went over. We didn't get to do a lot of coding, but we're getting there. Okay. We're getting there. And I'll see you on Saturday. Y'all have a great week, and I'll get this posted immediately or as soon as I can.